14 states of our country.
Oh, okay.
60 plus are from physics. 20 plus from chemistry.
Okay.
One from mechanical engineering, one from nanoscience and technology. So this is our group.
Okay. Total 80 you said, right?
Yeah, total 89, sir, but 73 regularly attending. Total 89, but 73 regularly attending. Out of 73, statistics are these.
But unless they attend some 90% or something like that, you will not give certificate, right?
That is what, sir. Actually, 90 plus people were there. Slowly, they dropped few people because of some reasons.
Okay.
So finally, we stick to 73.
Okay.
73 we can see online.
Okay.
Since this week, last week, entire last week, I received 73 assignments every day, so that I can say 73 are sticking.
Okay.
You can see also that the participants 73.
This is a little difficult. I have full screen. Participants 45 have come so far. Okay.
45 have come. Yeah.
Including us, I think.
No. We are in the panelist. We are in our list.
Oh, panelist is 3, and then attendees are 43. Yeah.
Yes, sir.
Okay. So otherwise, you are in JNTH Hyderabad only. I mean, you are.
Yes, sir.
Are you in deputation or you are transferred to here now?
No, on deputation. I am here in academic. Yeah.
Right.
Good morning, dear participants. So, welcome to this second week of our refresher course, and hope you have taken enough rest in weekend. So I hope all of you have done with your project, and we give a link to upload your project by afternoon, and in the evening we explain how to upload it into portal. So with this, I'll be introducing today's morning session's speaker. Dr. S. Srinath sir is working as a professor in School of Physics, University of Hyderabad. He received his bachelor's degree in physics from Usmania University, MPhil PhD from University of Hyderabad. He's worked as scientist SD in Institute of Plasma Research, Gujarat in 2001. He worked as a postdoctoral fellow at Organe National Laboratory, USA, 2002 to 2004, and University of South Florida, 2004 to 2006. Before joining School of Physics, University of Hyderabad in 2006 as an assistant professor, and he is a full professor in the School of Physics, University of Hyderabad since 2016. Coming to his academic and research achievements, he is an experimental condensed matter physicist. He has guided 3 and co-supervised 2 PhD students, mentored 4 postdocs, and is currently guiding 4 PhD students. Research interests include phase transition, critical phenomena, magnetoelectric coupling, magnetization reversal, exchange bias, magnetic anisotropy, magnetocaloric effect, transport and magnetotransport properties of multiferrics, spintronics, and nanomaterials. He published more than 100 papers in journals of international repute with H index of 28 and I-10 index of 52. And coming to other contributions of himself, he also serving as chairman University Cryogenic Committee and as director of IQAC University of Hyderabad. He has delivered talks at several national and international conferences. He is passionate about science, outreach and enjoys delivering extension lectures and talking about science to all audience, particularly school, college students. Dr. Srinath is a life member of Indian Physics Association, Neutron Scattering Society of America, Magnetics Society of India, Indian Cryogenics Society, KV Rao Scientific Society, and Indian Physics Teachers Association. He is serving as a referee for several international physics journals. His awards and honors: elected as Fellow of Telangana Academy of Sciences in 2016, Associate Fellow of AP Academy of Sciences 2013, and Honorary President of Pillalamari District Science Forum 2010 to till date, and he held various positions in different capacities to serve the people. Sir, with this introduction, I welcome you to this session, and I assure my participants that definitely you will enjoy Srinath sir's lecture, because I have attended about 4 refresher courses in our HRD center itself. He delivered 4 RCs. He delivered his lecture. So I fully stick to his lecture, and his lecture will be very much interesting. Definitely at 1 o'clock, you feel that you have done something and you have done, you have learned something in this morning session. Definitely that feel I will see in you in interaction session at 1 o'clock while closing sir's session. So with this, I welcome you to present your session, sir.
Good morning, everyone. Thank you, Dr. Vijay, for that nice and lengthy introduction. Maybe we can cut it down. We can probably just say that okay, I work in University of Hyderabad. People are interested. They can always now find out, right? Anyway, thank you for reminding also some of these things. Yeah, so I heard from Dr. Vijay that almost close to 780 participants from across the country are participating in this event. And I have also heard that majority of you are from physicists. I'm audible, right?
Yes, sir. Yes, sir.
Yeah. See, this is a refresher courses. I know, I mean, it is a mandatory on one side to attend because we need promotions and scales and all. But the most important thing I would consider is, apart from that, is to get acquainted with what's happening. Okay, especially if some of you are working in a college or a small place, affiliated place, where you may not have much access to the research facilities. So in that regard, again, I mean, I would suggest that I consider that refresher courses should always refresh us, not just, tire us. So I hope that I'll be able to refresh you with starting from very basic things in the first talk. I have divided my session into 2 talks. The first 1.5 hours, I'll be talking about nanomagnetism and applications, wherein I will sort of lay the foundations for the second talk to follow. So I will be giving very basic things, and then I'll go ahead with the current work which our laboratory is involved in at least one area of research. Okay, so called spintronics. So I'll spend some time on that area too. Participants are encouraged to ask questions. If you have anything, you can at the end of the session, or if you want to contact me either through email or something like that, you can always do. So my mail ID is Srinath, SRINATH, Srinath at UOHYD, University of Hyderabad, UOHYD.ac.in. So you can reach me for any clarification or questions. Okay. So with that introduction, I'll thank Vijay and JNTU HRDC for inviting me to deliver this talk of nanomagnetism and applications. Okay, so yeah, the plan of the talk is to motivation and introduction to nanomaterials. I'm sure most of you must be teaching for engineering as a part of, if you are working in engineering colleges or master's program students also, you may be teaching. So it may be a little repetition also, but then I look at it the way perception also changes, like how you look at it things. So maybe it will give you an added dimensions to the knowledge that you already have. Okay, so what is nanomagnetism? again, if you go and search Google or something like that, nanomagnetism, you may not really find appropriate definition or class of materials, but I will try to define what I mean by nanomagnetism in the course of this lecture. And how do we make these materials? Because the theme of this refresher course is both materials and physics. So I'll try to address both the aspects, in the sense how do we synthesize a material, how do we characterize a material, and how that we can lead to technological applications. So that's the kind of um, strategy that I'm going to adopt. Okay, so this whole thing, of course, is a very old work, but then this nanomaterials or nanomagnetism came into prominence, most importantly, by the Nobel Prize that is awarded to these two gentlemen, Albert Fert and Peter Grunberg, in 2007, okay, for their discovery of giant magnetoresistance. And so this application we are able to see immediately in our offices or at home, if we use computers in which the hard disk makes use of this principle. The data reading is read by a GMR sensor. So this is a direct application of the discovery that these gentlemen have made there in their laboratory. So it's actually, to start with, it's a very fundamental study. They did not think about an application at that point of time. Basically, they wanted to see how the magnetization can be understood, how when you grow thin films. Okay, so that is what their interest was. But then that changed that technology, that basically revolutionized the way in which we look at things. So and in fact, the Nobel Committee, in the citation to them, they said that GMR, giant magnetoresistance, can be considered as one of the first real application of the promising field of nanotechnology. In the sense, this is already, I know, in application. So we are all, knowingly or unknowingly, we are all already using this technology. So it has actually changed the way in which we store, we write, we can use the data. Okay, so that is what I wanted to say. And I'll of course introduce what is GMR and all. For physicists, probably you don't need, but then we'll spend some time. Okay, this is a very general definition. Nanomaterials, what you mean by that is okay, 10 to the power minus 9 or will be 1 billionth of in size, basically meters. Okay, one has to remember, okay, nanometers. So what size do you consider? It can be from 0.1 nanometers to 100 nanometers. What kind of materials? Materials can be anything. It can be metals, ceramics, polymer materials, or composite materials. So size does matter. Okay, normally there's a saying that how does the size change? I mean matter, but in these kind of systems, the size does matter, and we will see that how that is going to matter. Okay, so what is different? Okay, I have taken, suppose, some X material. That X material exists in bulk. Bulk, when I say, it is at least of the order of micron size. Okay, the dimensions are of the order of microns. It can be meters, it can be, I mean, very big particles. Okay, so that is what bulk. So the same particle, when I am reducing to a nano dimensions, when I am actually bringing it down, what is that it is changing? So as a physicist, I look at this way. What I say is the dimensionality is changing. That means when we look in the bulk, it's basically three-dimensional. That means I can actually extend the particles in all x, y, z directions. Okay, that is where we use your chronic Penny model or your periodic potential, your Bloch's theorem. So you are able to translate, like the way in which we'll sort of, you will take a unit cell and then construct and then make into a big crystal. So we are able to describe the physical properties because of the periodicity and translational invariance. So you are able to translate into three dimensions and then construct a bigger solid. So if you know about a unit cell, you are basically know about the solid, because otherwise it's impossible to deal with even 1 mole of an atom, which has 10 to one mole of a substance which has 10 to the power 23 atoms. Okay, we know that theoretical physicists, it's very, very difficult to solve any problem which is greater than a two body problem. Okay, when the moment you introduce more number of particles or atoms, then you have to go to approximate solutions. You will not be able to get a you cannot solve exactly. Okay, so that is the biggest problem that we have. But because of the simplicity that we have in terms of repetition and symmetry, in the sense in terms of a unit cell as an unit and then translating it with a particular periodicity, we are able to construct the complete structure solid. We are making things very simple and then able to do it in the bulk. Okay, but when you come to the lower dimensions, you do not have that luxury. That's what I'm trying to say. Lower dimensional, when I say, I'm giving you an example of zero dimensional. Zero dimensional means the particle is confined in all the three XYZ directions. So that means I will not be able to construct that the particle by some periodicity in the X direction, in the Y direction, and in the Z direction. So particle is localized in a particular space, a particular point in space. So that I'll consider as a zero dimensional object. Examples are nanoparticles. So if I consider a nanoparticle, okay, it's basically it doesn't have an extension in the area in the space. It is just localized at a particular point. On the other hand, if you consider a one-dimensional solid like nanorods or nanotubes, the particle you can extend it along, say, X direction. Let us say, okay. So that is one dimension. So I'm able to extend the particles. It has a finite length. It can be, say, 1 centimeter, or it can be a few millimeters. But if compared to the dimensions in Y and Z, where there is no extension, okay, the particle is completely localized. So in comparison to that, I can always say that this X direction, the particle is continuous. Okay, so this is the one-dimensional, which will constitute a one-dimensional object. Okay, so the dimensions in the X are not restricted or constrained, but whereas in the Y and Z directions, the particle is constrained. So the electrons cannot move now. So because there is no continuity, there's immediately a boundary. Okay, so it will not be able to translate. It will not be able to move along, say, Y and Z directions. Okay, that's what we are talking about. On the other hand, thin films are stack of thin films. It can be multi-layers. Okay, as long as the dimensions are of the order of 100 nanometers or so, or less than that. So what is happening in this case? In this case, what happens is, like, X and Y directions. Let's say take a one dimensional monolayer. When I say monolayer film is extending in the XY plane. Okay, but when it comes to the Z directions, there is no extension. Okay, so these again the same problem. Electrons cannot travel in the Z directions, whereas in the XY direction they can. If you apply an electric field or whatever you do, they can they will have mobility in the XY plane. Okay, so this object is called a two-dimensional object. So in nature, we can have a zero-dimensional object, we can have one-dimensional object, can have a two-dimensional object, which are all lower dimensionality, and the usual three-dimensional objects that we know of. Okay, which basically I can consider anything. Like I consider this object, which has a three-dimensional object, wherein there is a periodicity or there is a repetition in X, Y, Z direction. So this is like a bulk object that I'm talking about. Okay. Of course, physicists also talks about higher dimensionality and things like that, but let's not go into those details now. Let us just constrain ourselves to a three-dimensional object. And when I go and reduce the dimensions, what happens? Okay, so that is what I am trying to say. So one thing that happens is when you have consider a bulk object, of course, what happens is there are atoms sitting inside, okay, in the interior core, and also there are atoms sitting on the surface. But then when you consider the atoms sitting on the surface, then what happens is there the periodicity is lost. You understand? Because they do not have any neighboring atoms of the same kind. Okay, there may be air interfaces there. The coordination number is not the same. So the electron which is residing on the surface will not feel the same potential as an electron sitting inside the core, right? So surface is always a defect. That's what I want to tell here. Surface is always a defect. But then when you consider a simple solid state physics book like Kittel, most of the time we don't really bother about the surface atoms. We say that the bulk properties are still can be understood in terms of the unit cell and the periodicity. Okay, we'll say that, okay, this fellow has a BCC structure or FCC structure, and then this is the lattice parameter. So you sort of construct this solid, and then you have whatever potential that is experiencing by the electron at one point is experiencing the same thing with respect to that periodicity and then you are able to write the solution, and you can solve it, and then you can predict what are the physical properties, right? Even though know well that the surface atoms do not have the same kind of periodicity. So the surface atoms are, even though we know that the surface is a defect, so you cannot apply the same quantum mechanics with the same kind of block theorem. But then the number of atoms sitting on the surface are comparatively much smaller in comparison to the number of atoms sitting in the bulk. So when it comes to a bulk system, so then that is what I gave here. Like assume a spherical particle, the surface area of one particle with a diameter is given by pi d square, and the corresponding volume is given by this, and surface to volume ratio, if you calculate 6 by d, where d is the diameter, then you see that if d is of the sizable number, that's a big number, 6 by d is a small number. Surface to surface becomes a small fraction of the volume of the material. So the number of atoms sitting on the surface are much smaller in comparison to the total number of atoms which consists of this material. Thereby, the deviations are much smaller in comparison to, even if we ignore, okay, it still works, still solid state works. But when you go on decreasing the size now, the diameter, so much so that 6 by d becomes sizable, this becomes large. When as the d goes on decreasing, 6 by d becomes increased, it's very large. Or it's like, like you go on decreasing, and then at some point what happens is all the atoms are sitting on the surface. If you consider it like a football and then go on shrinking, then all the atoms are sitting on the surface. So there's nothing like interior, there's nothing like core. So the defect becomes important now. So I cannot explain or I cannot predict my physical properties based on the kind of luxury that I had with a bulk material, right? So that's where it becomes interesting. That's where this dimensionality comes into picture. So you tend to see the different properties. So it's not same as, like I take 1 kg of iron, or I take few nanometers of iron. It's not the same. It's not that the same properties are just scaled down. If it is so, it will not be so exciting. It will not be so interesting. But then because of these change in the dimensionality, the new properties can come, okay, so which are not experienced or which cannot exhibited by the bulk material, okay. And we all of us know, we have studied in quantum effects comes into picture. Suppose if you take two materials, very small interface, then they can actually tunnel through the barrier, okay. If the barrier height, barrier thickness decreases, okay, if it is of the order of few nanometers, the electrons can tunnel through the barrier, which also again people are using in devices, which I'll touch upon probably in the next slide or in the next talk. Okay, so we do see. So what is happening when you reduce the particle dimensions are that there is a lower dimensionality. Dimensionality is decreasing, using surface to bulk ratio is changing, and quantum effects are there. Okay, same thing I am showing here in the sense that, sorry. So you see that these atoms which are sitting inside has some coordination number, which I'm saying nearest neighbor number. So how many of these fellows are there? Now, if you go to a corner site, you go to the surface atom, then what happens is the number of atoms, the coordination is changing. So due to the increase in the surface atoms, the atoms are in close contact with other physical systems. Other physical systems, what I mean by that is, if I take a film, let us say a film like this, so what I'm trying to show is the atoms sitting on this surface are in contact with the air. Okay, so that is a different atom. It's not the same as the like I take iron film, let us say. Beneath this top layer, there is an iron atom sitting, but then above that, there is an air is sitting. This is like one interface. Another interface is if you consider a substrate, if you grow films on a substrate becomes again, different atoms, right? So the immediate layer which is sitting on the substrate will again have add atoms or another different atom in proximity. So because of this, what happens is that the interface they experience a different potential, okay. So, and also sometimes what we do is, if you are talking about magnetic films, mostly metal films, we put a capping layer. Capping layer is not to make them oxidize. That's very important. If I don't do that, suppose if I grow a film, iron film or nickel film or a cobalt film, which is magnetic, ferromagnet, And if you don't put any capping layer, what happens? Immediately it gets oxidized because surface area is more and the oxidation reactivity will increase and it can get oxidized. And what happens, the funny thing is the iron, cobalt, nickel, these are all ferromagnetic metals, but then oxides are antiferromagnets like iron oxide, nickel oxide, cobalt oxide, they are all antiferromagnets. So the magnetic properties are completely different, isn't it? So that is why we do not want that kind of a situation. So we normally put what we do is called a capping layer. So that means I'll actually deposit a film which is not reactive like a tantalum or something, platinum, depending on what I am actually interested in, or gold sometimes. So I can actually deposit a film, another film as a capping layer so that my film doesn't get exposed to the air or atmosphere. So, but with the process, what is happening? That the top layer of my film is experiencing now an interface, okay, with respect to this capping layer. So again, the potential is different. So if I take a mono layer, suppose if we just assume theoretically that there is a mono layer sitting on a substrate, and then on top there is also another capping layer. So what is happening? These interfaces is on both sides, these atoms are experiencing completely different potential. Okay, so the properties will be affected, whether it is electrical properties, magnetic properties, thermal properties, mechanical properties, dielectric properties. So depending on what system you are looking at in. That is why these materials are very, very interesting. Okay, so that means reducing the dimensionality or going to nano sizes is very interesting, not just in magnetism, since I am interested in magnetism, but in any field, which I just explained you. So many different people, optical properties, of course, are very much sensitive to the dimensions, okay, which we will show in a minute. So what is the take home message? Take home message is uh, is that actually, one second, is it blocking for you? Vijay, are you there? Hello. Yeah. Okay. So what is happening is a broken translational symmetry and change in coordination number, interface being different. So these are many things. I mean, some of the things. And also I told you that the imperfections and defects becomes more relevant because in a bulk we were ignoring, we were neglecting it. But when it comes to the nano dimensions, this becomes an important point. So that is what plays an important role. Okay. So one has to understand that also. Then as physicists, we normally worry about, the density of states, because if we know the density of states, it's very easy to calculate the average quantities at any variable point, because we know the density of states, then we do the partition function, how these atoms are distributed, what are the states available, and then how these particle electrons, let us say, are distributed among these states, density of states, then you can actually get average quantities. Okay, so you are able to calculate any physical property that you are interested in. You can calculate it if you know that then the density of states and the distribution function. So these two things are known, then you can actually calculate. But then what happens if you actually change the dimensionality? Dimensionality, if you change, it will affect the density of states also. Okay, in fact, you people can calculate this, take this as an assignment, and then try to calculate the density of states, which I'm sure you must have done for a bulk, which is like a parabola. Okay, so E versus D of E. So with respect to the energy, the density of states goes as a parabola, right, for a three-dimensional object. But when you go to sorry, when you go this is what actually I'm writing this three-dimension object also without confinement. What I mean by that is that the electrons are now free to traverse in both all the x, y, z directions, because the dimensions extend in all the three directions. So there is nothing like constraint. There's no confinement on the electron mobility. So that is what I'm writing is without confinement. So then the density of states is a parabola. But if we, for a film, like, two-dimensional case, which I discussed earlier, that objects are confined in one dimension, let us say in z directions, the finite thickness is there, which is of the order of few nanometers, so it is confined in the z direction, but whereas in the xy plane, the electrons now can, travel. So in that case, density of states comes out to be like, like a series of steps. Overall envelope would be a parabola, but then this would be a discrete steps. Okay, this would be the kind of a thing that we will have. And if the particle are confined in two dimensions, like a quantum wire, one-dimensional object, I'm going back to the previous slide where I'm actually talking about now different dimensionality, and then showing you that how the density of states will get affected when I reduce the dimensionality. So you see that in this case, it basically at this respective energies, En, okay, density of states is a series of peaks at those respective Ens. But on the other hand, if you go to a object confined in all the three dimensions, like a quantum dot, okay, where it is like, basically zero-dimensional object, in that case, it becomes like a delta function. The density of states looks like a delta function. So you see that by reducing the dimensionality, apart from whatever we discussed in the previous slide, the density of states itself is getting modified drastically. And if the density of states is getting modified, then correspondingly, the physical properties will also get affected. Okay. Yeah. So we see that. And then this is an example for optical properties. I'm sure most of you have seen Dr. Abdul Kalam used to show this again, nanotechnology by nature kind of a thing. So what is happening is the feathers, this is called structural color, as you know, that the feathers possess nanostructures of a peacock, and when light hits the nanostructures of the feathers, it is reflected off at different points, and the number of different light waves is reflected back. Reflected light waves interfere with each other, giving rise to such a beautiful pattern and beautiful colors. Okay, so this is, we not necessarily in the laboratory, but in the nature itself provides many of these examples for nanotechnology. Okay, so this is basically optical reflection, light getting reflected from these structures, nanostructures. They act like a gratings, and then because of that, constructive and destructive interferences, you will get what you get is such a beautiful pattern. And what I showed here is that man-made, like a gold or silver nanoparticles, when you make different sizes, you see that the usual bulk you have either yellow or white color, which basically, can get all different colors because of, again, light waves with different wavelengths appears as different colors. Some colors are amplified and some are cancelled out depending on the feather structure. In the case of this, same principle applies to this also. So this is a classic example of nanoparticles, okay, dispersed in some medium, so you will be able to get to this. So I could actually convince you from this example that by simply reducing the size, you are able to change the properties, for example, optical properties in this case, right? Then since my talk is relevant to magnetism, I want to also tell you that how changing dimensions or changing size or different length scales will determine the magnetic properties. Okay, why is it interesting? So when you come to what I'm trying to show here is, this is a table from a book by JMD Coe, wherein he compared, different length scales which are important in magnetism in terms of, you see, this is a nanometer length scale. Okay, so you see that many of these length scales that are important for magnetism are in the nanometer dimensions. For example, the exchange interaction, which actually is responsible for ferromagnetism or antiferromagnetism in a material, is of the order of 1 to 0.1 nanometers. Okay, the range of interaction. This is called a very short range interaction, wherein the electron wave functions in the neighborhood, they will overlap either constructively or destructively, depending on whether J, the exchange integral, is positive or negative, giving rise to ferromagnetism and antiferromagnetism. And then even the long-range RKKY interaction is, which is also responsible for magnetism, is of the order of 0.1 to 10 nanometers. And the domain sizes typically are of the order of 10 to 1000 nanometers. And some of these things I will actually explain as we go. And electron mean free path, this is basically of the order of 1 to 100 nanometers, which is actually responsible for transport. Okay, how even otherwise they will encounter collisions, and then you will see that resistance will increase. So these kind of different properties, transport and magnetic properties, have the ranges in the range of nanometers. So that is why when you actually reduce the particle size to nanometers or film size thickness to nanometers, these length scales are important, and then they change the properties. Okay, so that is what I wanted to convey here. Then next a few minutes, because this is a course on materials also, I'll try to, this I think we can skip through quickly because most of you must be teaching already these kind of things. That how do we actually make these nanoparticles? Are two methods. One is a top down, basically you take, what I'm going to show is I'll try to spend a couple of minutes on how do we synthesize, and then how do we characterize a few minutes, then go to physical problems and then explain, I mean, take examples from research. Okay, so top down is we take a large particle material and either mechanical or chemical methods, like you can use laser ablation, or you can actually use a ball milling. So you actually grind them with energy, high energy, balls, so that you can actually churn them, the particles, into nanometers. So you are actually trying to reduce that into very small particles. Or bottoms up is basically you can actually assemble now, take atoms or molecules and then assemble them into nano dimensions of required dimensions. So you take to produce nanoparticles, nanotubes, thin films, you can actually grow films and things like that. So there are different ways, and some things which we also discuss is there in general, preparation methods, physical vapor deposition, which we are doing elaborately in our group. So I'll spend some time on that. And then chemical vapor deposition, electrode deposition, sol gel, ball milling. So ball milling is what I told you about, no? High energy balls. You can actually churn the particles and all. Sometimes people use of natural particles. So there are different ways to get you nanoparticles of interest, nanomaterials of interest, and you want to study, right? Physical vapor deposition, just to put it in a nutshell, it's nothing but you take a solid material and then somehow you vaporize it. Okay, so you generate a vapor phase, and this transport this vapor onto a substrate on which you want to deposit the film. So it's only two-step process. Okay, you sort of take the material, vaporize it, and vapor has to be transported onto the substrate, and then you get a film. But it'll have a very elaborate machinery. In fact, the process, because of the fact that you need vacuum, very very important. Why? Why? Because first thing is, uh, I mean, contamination is one issue, but that's not the main issue. Contamination is basically what I said is earlier also, that you do not want the material to be oxidized and things like that. So you need to have a controlled environment. Okay, you need to have a chamber in which when you are depositing a film, you need to control the vacuum. Okay, you have to have a very good vacuum, and then if you still want some nitrogen or argon or something, the gas you want to can put in. But mostly you would like to have a very good vacuum. Why? Why? Because of the fact that the atoms which are into a vapor phase should go all the way to the substrate. Otherwise, what happens is, if you're trying to do it in ambient pressure, because the mean free path is of the order of few nanometers, so then the particle will never be able to reach this substrate, which is at a distance of few millimeters to centimeters from the target. So what you need is, the first important concept, I mean, point is that the mean free path of these atoms will increase. Okay, will be if you decrease the vacuum. I mean, you increase the vacuum. That means you actually decrease the pressure. So by creating vacuum, you are able to transport the material onto the substrate. That is where actually bulk of the your thin film chamber consists of. It will have pumps. It will basically gauges to measure the vacuum and things like that. Okay, so if you divide into two parts, one is the vacuum component is one aspect. Another component is how do you make the target into a vapor phase. So these are the two important concepts which are involved. It can be anything. It can be a pulse laser deposition. It can be a molecular beam epitaxy, or you can have sputtering. You can have a plasma deposition. You can have electron beam evaporation. You can have a simple thermal evaporation. So all these processes that I discussed here, I mentioned here, they all rely on physical vapor deposition technique. Okay, so I'll spend some time on this. Like, for example, sputtering is nothing but is a process whereby atoms are ejected from a solid target. As I told you, like suppose you take a target and then there is an ion gun, and then these ion guns are used to eject the particles. So these particles will now traverse and then form onto, as a film onto the substrate. Okay, so this is kind of a thing, and you can actually use also, like pulse laser deposition, where you use a laser beam in order to evaporate this substrate target, and then that laser plume basically that will consist of this material. This material now gets transported onto the substrate and then form a film. So this is the whole thing is done in a vacuum chamber. So as I told you, you have a vacuum chamber, and the sample you can have, I mean, more, the basic requirement is this, but to make the film more homogeneous and to have a better control and things like that, you will have a sample stage where the sample can actually, translate, so that you don't get non-uniform thickness of the film. Because when you are actually, that the shortest distance is the straight line path, so then there is a more proper probability that the atoms will actually get accumulated here, so the film becomes more thicker here in comparison to here. Okay, so to avoid that kind of a situation, what you can do is you can actually translate this flow, this sample stage, so that you get more and more or less uniform thickness. Okay. On the other hand, you can also rotating target, because what you do is, if you don't do that, then you go on bombarding this flow with respect to ion beam in the previous case, or a laser beam here, then the material at the center will only get ejected and most of the target is unused. So to avoid that, what you do is actually you rotate the target also, so that you are actually exposing, you are uniformly, I mean, more optimally you are using the target. So these are like tricks and trade of the trade. But otherwise, it is a simple vacuum chamber and you operate the film and then gets deposited. And most important thing, again, another important thing is that you need to have a monitor what about the thickness of the film. So they're not usually, like, you can have a quartz crystal oscillator, which will resonate at a particular frequency depending on the mass that is of the crystal. So when you deposit the film, so film also gets deposited onto the crystal, and then due to which the frequency, resonating frequency of the crystal will shift. And by reading that, you can estimate how much material is deposited onto the crystal, and assuming that similar material is deposited on the film also, you'll be able to determine what is the thickness. So this is all calibrated. Before you can actually calibrate it, and directly you can get in terms of the thickness of the film. So you can actually determine, you can deposit the known or the required amount of the thickness of the film. Okay, of course later you can take it out and then do a number of studies, and then you can actually independently determine the thickness and things like that. But then during the deposition also one can monitor at least, and also try to control the thickness of the film. So these are some techniques which we use. And people also use no, sol gel, simple chemical methods, in order to, because these are thin film deposition methods are, of course, expensive and difficult to, in comparison to the cheap sol gel process, where you can actually make formation of oxide network through polycondensation reaction. So what you do is, sol is a stable dispersion of colored particles, polymers in a solvent, and so you can use this is to dissolve the compound in a liquid in order to bring it back as a solid in a controlled manner. So whatever material you want to deposit, you have to controllably dissolve into a liquid and then precipitate it in terms of a solid material. And so this is generally a low temperature synthesis, wherein you can actually control the particle size much better. Because what happens is, when you grow, in the previous cases, when you actually deposit the film or use a solid state method, most of the time what happens is, for the reaction to take place, you need to go to very high temperatures, especially solid state method. And to get the crystalline structure, again, you need to anneal them at very, very high temperature. So if you do that process, in the process, the particles will normally get, they grow. So because of the thermal expansion and because of the reaction kinetics, that the particles can come together and then coalesce and then become a bigger particle. So in the process, controlling the size of the particles becomes a challenge when you go to a solid state method. But in the case of a sol gel method, what happens? The advantage is, because the reaction is taking place in a solution, so you will be able to control it much better, and you don't really need to go to very high temperatures. And if you want, you can add something like a surfactant, where this fellow gets coated onto the nanoparticle, so that these particles, they don't come together and agglomerate and then become a bigger particle, so that the particles can be actually, controlled, size can be controlled and things like that. So we, in our laboratory also, we do these things routinely. So you can actually, and also there is another process called hydrothermal, very similar to your pressure cooker. So you actually, create pressure, and then because of the pressure, that the reaction takes place at a much lower temperature in comparison to the solid state methods. So using a hydrothermal method also, one can actually control the size of the particle. So in the sense that there are different ways in which you can use in order to prepare your system, the system which you want to study, okay, in nano dimensions specifically. Then what kind of a material you can take? You can take simple elements, as I told you, like iron, cobalt, nickel, and things like that, or you can take combination of elements, or you can take new materials you can actually construct, like, like bulky balls and nanotubes and things like that. So there is no hard and fast rule. There is no, like, strict rule that, okay, you can only make this material as nanomaterial. No, you can in fact make every material as nanomaterial. Of course, you need to choose the right preparation method in order to make them, synthesize them into a nanomaterial. And then once you make a nanomaterial, we know the next step would be to characterize them. So we use typically X-ray characterization. If you want to know the crystal structure, you want to know the lattice parameters, you in fact want to know even idea about any impurity phases or stoichiometry to start with. So many things. The strain in the film can be, or strain in the material can be measured. So there are X-ray diffraction or X-ray characterization is one of the primary characterization techniques, which every sample that you make, you need to do it. So that is what everyone does it. But if you are interested in magnetism, you can consider trying neutron diffraction also, because a neutron has a magnetic moment. So unlike your X-ray photon, which basically gives you only the atomic density, so you in the neutron diffraction, you will be able to calculate, in fact, determine the magnetic structure also. You can say whether the magnetic material is ferromagnetic or antiferromagnetic. Especially antiferromagnets, it's very difficult to characterize them using bulk materials, whereas neutron diffraction gives an unambiguous magnetic structure. Of course, it's very expensive, and you cannot do it, and it's not a laptop experiment. You cannot do it on a benchtop experiment in the laboratory. But whereas you have to go to big facilities like BIRC in order to do it. But then if you are have a research problem is really good and you want to determine the crystal structure, you can always get beam time and calculate measure neutron diffraction. In our laboratory, since we are interested in studying the magnetism, we also make use of the neutron diffraction studies. And what kind of information you can get? You can in fact get grain size, structure, residual stresses, atomic density, and many more things. Actually, this is just a snapshot of things that can. Basically, what you are trying to do is you are trying to structurally characterize the material. And surface techniques, of course, you can use TEM, SEM, STM. These are all microscopic techniques, because if once you make even X-ray, you do it, most of the time what happens is referees will say that no, and also journals will want nice pictures. So they would like to have a TEM picture or a scanning electron microscopy picture, which of course, apart from giving you tells you the shape of the particles and size of the particles, which can SEM, especially if you have EDAX as a probe, which is basically energy dispersive spectroscopy. So you will be able to determine what is the chemical composition. Okay, what the material consists of. Okay, and what you can say is that what is the and what is it, what proportion this the composition is there. So you can in fact get the stoichiometry of the material. So you can determine all this from surface techniques. This is a setup we have in our school, which is scanning electron microscopy. We can image this sample surface by scanning it with a high energy beam of electrons. Electrons will interact with atoms that make up the sample, producing signals that contain information about sample surface topography, composition. This is very important. So you can in fact determine the composition also. Okay. So you can determine the size, shape, and composition of the material using SEM. Since I am interested in magnetism, so immediately we'll try to go to magnetic material information. So we'll try to measure magnetization. So in general, we measure magnetization as a function of temperature. That is called MT measurements, magnetization as a function of temperature, or magnetization as a function of magnetic field, which is called MH measurement. And from there, we can actually get magnetic moment and magnetic transitions, especially if there is a ferromagnetic paramagnetic transition. I can determine what is the TC of the material and things like that. So this is very interesting in order to characterize magnetically. So techniques which are used for magnetization measurements are either depending on the force that the material experiences because of the magnetic field, which is called force method, which can be used. I mean, the instrument which uses this principle is called Faraday balance or Gauss balance. But mostly people are using now flux methods, which are vibrating sample magnetometer or squid. Simply putting it, the magnetic particle acts like a dipole, and this dipole is now oscillated in a static magnetic field with a particular frequency using a transducer. So this fellow is vibrated with a small frequency of the order of few hertz. Then what happens is there is already a magnetic field, DC magnetic field, mind you, provided by an electromagnet. Okay, you have a coil and you pass a current and you generate a magnetic field. In this magnetic field, this magnetic dipole is oscillated with a small amplitude, due to which there is an EMF which is generated, which is nothing but your Faraday's laws of induction. And this induced EMF is picked up by the pickup coils here. And these pickup coils now will tell you that, of course, this voltage that is induced in these pickup coils is proportional to the amplitude of vibration, frequency of vibration, and also magnetic moment of the sample. Since we are keeping the frequency and amplitude constant, so this is proportional to the magnetization of the material. So you can actually determine the magnetization. Of course, one has to calibrate it. Once you calibrate it, there are standard samples which can be used, and now it is like, you can calibrate it and then can directly convert into EMU, electromagnetic units, and EMU per cc is nothing but your Gauss or Oersted. So you directly get in terms of magnetic units. Okay, you can actually do that. So the same principle, this is a VSM, maybe you can be used here, except that this particular system that I'm talking about is called PPMS, Physical Property Measurement System, designed by Quantum Design. Is a company which provides this. Of course, there are many other fellows who does the similar kind of a thing. The advantage in this system is that this has a superconducting magnet. Okay, so magnetic field that you can apply or can generate is of the order of few Tesla. So normally, if people have gone all the way up to 22 Tesla and things like that, what we have is we have a 7 Tesla magnet, and also we have a 9 Tesla magnetic field. So you can actually use that, and then sample, probe goes inside this cryostat, so that you can actually change the temperature and also magnetic field. So you are able to now change, you can map, okay, you can at different temperatures by applying magnetic field, you can measure magnetization, or at a constant magnetic field, you can change the temperature and measure magnetization. So similar, both can be done. So using this kind of a experimental setup. This is a squid magnetometer. Again, you can have both temperature and field as a thermodynamic parameters and measure magnetization. And for this cooling superconducting magnets, we use liquid helium. So we have a helium plant, and we produce liquid helium and then try to cool these superconducting magnets and then measure magnetization as a function of temperature and field. So magnetic field, you can apply plus or minus 9 Tesla. 1 Tesla is 10 to the power 4 Gauss. Okay, just to put in perception, like, Earth's magnetic field is of the order of 0.32 Oersted. Okay, so you see that 1 Tesla is, orders of magnitude much higher in comparison to the simple Earth's magnetic field that we talk about. See, and the temperatures you can, because we are using liquid helium, easily one can go from 2.5 Kelvin by applying pressure on the liquid helium. In fact, one can go up to 1.8 Kelvin, but routinely we go from 2.5 to 350 Kelvin using a standard setup. And they also provide a high temperature setup through which one can go up to 1000 Kelvin. So using an oven. And you can measure magnetization as a function of field and temperature. So the samples, what kind of samples? Samples can be powders, pellet, thin films, any sample. Sample holders we use depending on, of course, what kind of a sample and what is the magnetic movement of the sample and things like that. There are different types of sample holders available, and the accuracy they can measure up to 10 power minus 6 to minus 7 EMU. Okay, so that is a kind of a setups that we have. And for, of course, even liquid helium when we are using, we need a pre-coolant liquid nitrogen. Otherwise, the helium boil will be very, very expensive. I mean, helium is very expensive, so we need to preserve as much as helium possible. So we use a pre-coolant liquid nitrogen. And also the helium which is actually used in this, after boiling, the gas is collected through here, and then all this gas is collected back and put it into a bag, and then that we compress that gas into the cylinders and then again reuse it for generation of helium, liquid helium. So in general, we have something like 85 to 90% efficiency, so that we can actually, otherwise it becomes prohibitively expensive, to have liquid helium and then use it. In fact, I just want to tell you that if you go to MRI machines and things like that, they use NMR machines and all, they use superconducting magnets, MRI machines. And for that also they use liquid helium. Okay. But there what happens is the liquid helium, they don't really change so much of the temperature. It is always kept at that temperature and then you are measuring. So you don't boil up so much. So if you fill it up once, 3 to 6 months, depending on the usage, you are okay. Right. But then most of the cost that you are bearing today for your MRI scan is purely mostly for, of course, initial investment for magnets and things like that, but the running cost is mostly for the liquid helium because we do not have any superconducting material which can operate even at liquid nitrogen temperature. Okay, so if and when we can get a material which can be operated at liquid nitrogen or room temperature, then the MRI cost will drastically go down. So you can see that how the technology or scientific discoveries can change the quality of life and also the economics involved in that. Okay, so that is something which you people should know, and also motivate the students so that they know that what we are doing is actually worthwhile. It's meaningful. Okay. Okay. Any questions at this point of time? I'll just take 2 minutes here in the sense to get some any chat box, anything. Any participant? I mean, is it okay? Am I audible? One of you have to volunteer. Hello? Hello?
Yes, sir. Yes, sir.
Yeah, okay. Everything is fine, right?
Yeah, everything is okay, sir.
Okay, okay. I'll continue. Right.
Yeah,
Yeah.
please.
Okay. So this is again having told you that how you prepare the materials, how characterized, and spends next few minutes on magnetism. So magnetism is very, very important. And in fact, there is a saying by one cartoon character, Dick Tracy. He says that the nation that controls magnetism will control the universe. In fact, it is very, very true. Okay, we live up. Like you must have noticed, you can go to any toy shop. You want to buy toys. Okay, mostly movable toys. Let us say battery operated movable toys, and there's a magnet eventually in that. I mean, definitely. And and you see that it's mostly made in China. Right? So why is that? Why can't we make toys? Can't we make toys? Yes, we can. But the point is, the magnets that are used there are mostly powerful magnets to get this kind of thing. Any question? No. Okay. So if these and then the rare earth magnets are actually, the abundance is much more in China in comparison to rest of the world. Okay, they have a large reserves of rare earth magnets. So it becomes economically much cheaper for them. Of course, the cheap labor and production cost and things like that. So the market, so they are able to, flood the market with respect to flood the world rather with respect to these kind of things. So magnets, but we have no choice. I mean, we want to use it, we have to import and we have to buy. So if we can get a material, if we can get magnets which are cheap, then in fact we can also rule the world, right? So that is the important thing. So magnetism is very, very important. That's what I want to tell. In fact, I teach, I do not know, most of you participants are across the country, but we have in our MSc program, in a solid state physics specialization, we have a complete paper devoted to magnetism, wherein 4 classes per week. So saying that almost 60 classes I teach magnetism. So in the sense that just because it's so important. Okay. So and also this is one of the first kind of a material or sensor which mankind has found. Okay. For navigation purposes, people have used. And so to understand the nature of magnetism in these materials, people have come up with a lot of theoretical models and understanding. So that is helping to apply the similar kind of models in other fields also. So in the sense that if you know magnetism very well, you can actually understand many things in other areas of science too. So that is also another apart from just the technological applications, but then the principles or the theoretical understanding of magnetism also is very, very crucial. Okay. So if you just, this is, I use it for students, but I'll just show that you can, magnets are there everywhere around around home. Okay, you for your transmission, energy production, energy transmission, any movable part that you can think of, inside motors, so cooling fans. This slide I always show this. So you see that a car, automatic car, has whatever is marked here has a magnetic component. Okay, but this is, I would say, is like 25 years old picture. If I take a modern car, probably I will not be able to even map up. Okay, because there's so many sensors now, right? So all these fellows have magnets inside. So you can see that the magnets are playing an important role for energy production, energy transmission, and for all your motors, and for all most of the sensors that you use. Okay, so for example, your storage media now. Okay, your storage media has increased quite a fold. I mean, any number of times. Again, I just give example that during our PhD, I'm sure some of you, I'm probably much older than you guys, participants. But anyway, so we were having only, like, what is the 256 kilobytes hard disk, which was almost of the size of a notebook, 5.5-inch diskette, okay, of this size, and which was having a storage capacity of 256 kilobytes, right? So whereas now you see, you talk about gigabytes memory, okay, terabytes memory, in fact, okay, even storage density. So this is all magnetic storage density. It has increased. This is again partly because of the nanotechnology advances, partly because of the GMR. We are able to read the information. You are able to store the data, okay, in terms of binary data, in terms of spin up and spin down. So this is purely because of the two things. One is the advancement in materials and advancement in technology, and then combining this together, you are able to actually make it revolutionize. In fact, all of us have studied about Moore's law, that the number of transistors that the chip can accommodate, will grow, will double every 18 months or so. The magnetic storage density is in fact increasing much more faster than the Moore's law prediction of semiconductor transistors. So you can see that magnetic materials are actually growing leaps and bounds. And also you can see, if you go to market today and then ask for a storage density, a storage device, go to the market next year, you will get double the density, double the storage capacity for half the price. In fact, because the production is increasing, the technology is increasing, the product material that is used is decreasing, and the price is decreasing, whereas you are able to store more and more data. Okay, so that is all is because of the thing. So this is important, but then they are used in across many things. I think many of you are from physicist background, so I can skip these fundamentals of magnetism, in the sense maybe 1 minute tutorial that we can talk about. In the bulk, we talk about diamagnetism, when you have unpaired electrons. I mean, so when all the electrons are completely paired, so then you see that the only magnetic moment that is induced movement because of Lenz's law, so that susceptibility is negative. Okay, so that kind of a thing. And a paramagnetism are materials where you have unpaired electrons, but then they are not interacting, so they respond independently with respect to the field. So you have a positive susceptibility, but then because there is no interaction between the spins or the magnetic moments associated with the unpaired electron, they will not exhibit any hysteresis. In fact, the magnetic M versus H would be linear, and when you switch off the field, the magnetization goes to zero. So in the sense, they do not have many practical applications per se based on the paramagnetic effect. Okay, so but these ferromagnets where we are interested in, there, of course, how ferromagnets will behave that way is because of the quantum mechanical exchange interaction. But essentially, you have unpaired electrons, and these unpaired electrons have a permanent magnetic moment, possess permanent magnetic moment, and these magnetic moments, they interact with respect to this exchange interaction. And so that depending on the nature of interaction, either they will order parallel to each other, giving rise to ferromagnetism, or anti-parallel to each other, giving rise to antiferromagnetism. Okay, so this kind of a thing is important. So this what gives you exchange interaction. So which all movements have a positive component along the direction, and you have, I mean, if one step, one point definition of ferromagnets is that the materials have a spontaneous magnetization. So I don't need to really apply any magnetic field Because of the interaction, spontaneously these movements are all orienting along a particular direction, giving rise to a net magnetization, which we call as spontaneous magnetization. But of course, what happens is the thermal energy, the temperature is trying to randomize this. So there is a temperature up to which this spontaneous magnetization will be finite. And above that, these temperature will try to randomize these movements, and then thereby in the net, there will not be any net magnetization. And that temperature at which this interaction energy is equal to the thermal energy, and beyond which their movements are not now really correlated, or they are not coupled. So that temperature is nothing but the transition temperature. So you have a ferromagnetic low temperature to a paramagnetic high temperature phase transition, right? So similar thing, as I told you, if the interaction energy is such that, I think I'll show this in a minute. In antiferromagnets, for now, you can say that these movements are coupled anti-parallelly, so there's no spontaneous magnetization. But when you apply a magnetic field, of course, they will have a magnetization, net magnetization. Okay, so both of them, because of the interaction, will show hysteretic behavior. So you see that M versus H is hysteric behavior. Ferrimagnets are materials where you have magnetic moments interacting coupled anti-parallelly, but then the magnetization at a given site, all the sites are not equal. Thereby, the moments, let us say loosely that the moments which are orienting along one direction parallel, plus Z, is more than the minus Z. So there is a resultant magnetization which gives rise to ferrimagnetic ordering. Okay, so there are different kinds of ordering. Why am I talking about this? I'm talking about this because depending on this type of order, the material will have applications. As I told you, like, when the paramagnets, just based on the magnetic property, there are not many applications, because the once you switch off the magnetic field, the magnetization goes to zero. So that's where we are actually looking at ferromagnets or ferrimagnets. Okay, I'll try to differentiate these two also in a minute. So we'll choose a material based on the kind of physics. But where are we talking about? All this we're talking about in bulk, right? Because this is what we studied. So what happens when you actually decrease the particle size? Oh, before that, we'll also consider in terms of bulk. I just want to introduce a domain picture. I'm sure most of you know, but it's important to understand once again that if you see iron, okay, it is 1043 Kelvin is the TC. In fact, it's greater than 1000 Kelvin. But if you see a nail on the road, most often what happens is this material will be non-magnetic. It will not show any magnetic property. It will not show any attractive property, right? So why is that? Even though TC is much higher, that means it should have been ferromagnetic. Why is that it is not showing any magnetization? That we know that is purely because of the domains. Of course, it is ferromagnetic. There are regions in the iron where the spins are all parallel, but then that region is called domain. But then these domains themselves can be oriented in different crystallographically equivalent directions. Okay, so that is where the anisotropy comes into picture, which I will touch upon. Okay, so what decides the order? What decides these spins, how they have to point? So actually, in the absence of external field, I told you, right, spontaneous magnetization. So your magnetic movements are oriented along a particular direction. So what decides that? So that is decided by this expression called the total energy, which consists of different terms. For example, the exchange energy. Okay. Say, you may ask, what is exchange energy? Exchange energy is nothing but it is a Coulomb interaction, Coulomb energy, like the way in which you talk about between the two charges, but then modified by Pauli exclusion principle. That is very important. Okay. So depending on the spin orientation, okay, either the spin can come much closer, or there is a certain distance between them. Okay. Otherwise, if they have to be anti-parallel. So this exchange integral is, we call this as J, and J can be positive or negative. So that is decided by basically what is the the distance between these spins, something called Rij. I and J, let us say 2 points, and Rij is the distance between the ith and jth spin. So Rij will decide, that means two atoms, how close or how farther they are, and that will decide what kind of a interaction they will have. Suppose Rij is very, very small, okay, then the spins cannot have the same, both the electrons cannot have the same spin because of your Pauli exclusion principle, that one of them have to have an anti-parallel configuration. So that is when If you plot J versus Rij, you see that for very, very small distances, the Rij J is actually negative. Probably I will have that slide in a minute. So that J, if J is negative, then this is nothing but the exchange integral. If it is negative, this exchange Hamiltonian is actually given by a term called exchange Hamiltonian, which is called minus 2j ij si dot sj, where si and sj are the spins at site ith and jth site. Okay, if j is negative, so there is already a negative sign. So si dot sj should always be should also be negative. Only then the total energy can be minimum. So that means these spins have to be anti-parallel, because this is a dot product, so it's a cos theta. Cos theta is cos 180 is minus 1. So J and I have to be anti-parallel if I and J have to be anti-parallel, or Si and Sj have to be anti-parallel if J is negative. On the other hand, if J is positive, let us say if the spins are, the exchange integral is such that J is positive, then they can be parallel. They are parallel, in fact, because minus 2j ij si dot sj. So j is positive, minus is already there. So si dot sj cos 0 is 1. So that becomes minus 2j. If I say that spin at site I and j is equal to s, so that energy becomes minus 2j s square. Okay, so that would be the maximum negative allowed energy. So that will prefer the spins to have a ferromagnetic interaction. So you can see that the exchange actually decides what kind of a orientation the spins can have. But then it will not tell you which direction they have to point. Listen here for a minute. What I'm trying to say is, exchange cell tells you that the spins have to be parallel. But then which direction? That exchange will not bother. It will not tell you. It can be any direction in space as long as they are parallel, if J is positive. So this is like isotropic. So exchange will tell you that the spins have to be parallel. So, but you know that magnetization is preferred along a particular direction. If you just simply measure any textbook you see that that there are easy directions and there are hard directions for magnetization. So that means certain directions are preferred wherein the magnetization is easy to magnetize or demagnetize. Okay, so from where it is coming? That is coming from the magnetocrystalline anisotropy, which is called EK. So you have another term called EK, wherein that will tell you that there are certain directions along which the magnetization prefers to orient. This is called magnetocrystalline anisotropy. Okay, I'll give some examples. And the third term is the magnetostatic energy. This I will explain in the next graph. So I'm actually explaining now magnetostatic energy. So what I'm saying is, assuming that magnetocrystalline energy is uniaxial. What I mean by that is, if you take a hexagonal crystal, okay, such as cobalt, so there is a certain directions, let us say C axis. The spins are easy to, they prefer to orient along C or anti-parallel to C. So there are two directions, mind you, like plus Z and minus Z, the spins prefers to orient, but along an axis. So this is called uniaxial anisotropy. So a hexagonal crystal has a uniaxial anisotropy. Whereas if you take a cubic crystal, let us say I'll take a cubic crystal. For example, in the cubic also specifically, let me say BCC, body-centered cubic. In the body-centered cubic, what happens is it has actually cubic anisotropy, or 6 equivalent directions in which the magnetization can prefer. What are they? They are along 100, that means along the cube edge, along 100, that means along x-axis, like 100, 010 along y-axis, or 001 along z-axis. And opposite to that, 1 bar 00, 001 bar, 001 bar 0. So there are 6 directions or 3 axes. So a BCC BCC crystal, for which example is iron, has cubic anisotropy. So that if I plot in any, if I apply a magnetic field, what I mean by that is, if I apply a magnetic field along any of these directions and measure magnetization, then the energy that is involved is the same. That means that magnetization that I can develop for a given magnetic field at a given temperature is the same. It doesn't really depend. But any other direction, suppose if I plot along the body diagonal or a phase diagonal. In this case, actually in iron, for a BCC system, the phase diagonal, if I apply a magnetic field along the phase diagonal, then it is called intermediate energy, wherein neither it is too small nor it is too large. So it is not easy axis, which we discussed for along the cube edge 100 and all. So that is the easy axis of magnetization. But phase diagonal is the direction in which the magnetization, you need to apply more field in order to magnetize to the same energy. On the other hand, body diagonal, 111 or 1 bar, 1 bar, 1 bar, along that direction, it is hard direction. So you need to apply a large field, because spins, they don't prefer to have, why? Because of the spin orbit interaction. Okay, that again, too many details, but let's not go into that now. Let us say that, but because of this spin orbit interaction, the spins do not prefer to orient along the, say, body diagonal. But I can do it. What I need to do is I need to spend more energy. That means I need to apply more field, so that the magnetization grows slowly and then finally eventually it gets saturated. So that is called hard axis of magnetization. So spontaneously, when the system is magnetizing, that means because of the interaction, because of the exchange energy, the spins are pointing, magnetizing. I mean, they are polarizing or orienting along a particular direction. They prefer to orient along the directions in which it is easy to orient, given by the crystal structure. So if I define a crystal structure, there are certain crystallographic directions in which the spins will orient. So this fellow will tell you that they have to be parallel. But parallel in which direction is given by EK, magnetocrystalline energy or magneto. So this energy tells you that, okay, if it is a hexagonal crystal, then it has to be along C-axis or opposite to that. If it is a cubic crystal, BCC, for example, it has to be along the cube edge. Okay, if it is a FCC crystal, then it has to be along the body diagonal. So these are basically given by the crystallographic orientation and their direction cosines. So one can actually do this calculation. It's very easy calculations. If any participant is interested, he can write to me. I'll suggest you a standard book from which you can actually determine how the magnetocrystalline energy can be decided for different crystallographic structures. Okay, so you can actually determine. So I'm going to discuss now the magnetostatic energy, wherein suppose that exchange, I told you that exchange actually tells you that the spins have to be parallel, and I'm considering hexagonal crystal for simplicity. So that means it has a uniaxial anisotropy. Okay, so if I am doing that, then spins basically are pointing along, say, first picture you consider, don't consider this now. First time picture, if you consider, then what happens is all the spins are pointing in this direction. If the spins are pointing in the direction, like we can say that, like, bar magnet, like north and south pole, you can always say, like an electron, like current carrying loop is nothing but a bar magnet. You can always, the magnetic field associated with that can be visualized as a bar magnet. So then I can say, okay, there is a north pole, there is a south pole, similar to our bar magnet. If you do that, then what happens is, if the magnetization is pointing in this direction, normally we'll say that, okay, these are north poles and these are south poles. But you see, inside the sample, inside the specimen, inside the solid, magnetization is pointing in this direction, okay, from south to north. That's the convention that we use, right? Okay. But then there is actually a residual field, or actually the field which actually is coming out of the specimen because of the induced poles. See, I have not applied any external field, mind you. This is only due to the interaction that the spins are pointing along a particular direction. So the magnetization in this direction. So this fellow, what it is doing is, now because of the induced poles at the surface, you see that field, of course, magnetic field lines have to close. Okay, there's no, I mean, that is what your Maxwell equation tells, right? You do not have a single monopole because of this problem, that divergence of B is actually always zero. So it has to enclose, it has to close down, right? So the magnetic field lines now have to close, but then how do they close? From north to south. So you see that the field lines which are emanating from the surface poles by the magnetization of the specimen is in a direction opposite to the field, internal field. You see that this field is opposite to the internal field, right? So, okay, let me put it this way. Let us say that the spins are all pointing in this direction, parallel to each other, and then in the process it is getting magnetized. Okay, if these fellows are all random, then the net magnetization average would have been zero, isn't it? This has magnetization purely because of this orientation. And so I'm saying that this orientation is causing the specimen to get magnetized. Okay, so this is magnetization is growing up or magnetization, there is a fixed magnetization. But then because of these individual poles, which is actually having opposite direction, it is the net effective magnetization seen by this fellow at a certain distance is small, because these two fellows, one is pointing in this, another fellow is actually down, so the net magnetization is zero, small. So this fellow, I can say that this is like a demagnetizing field. So what the field that is actually emanating out is called demagnetizing field. So you see that this demagnetizing field is nothing but your magnetostatic energy. Okay, so if you have a more demagnetizing field, the net energy, even though exchange is minimum because the spins are all parallel, even though EK is minimum because the spins are pointing along the easy axis of magnetization, because of the large magnetostatic energy, total energy will increase. So the energetically it is not favorable. Okay, that minimum energy, I mean, the system will acquire a configuration for which the total energy is minimum at any given temperature. Okay, so system cannot have a minimum energy configuration because of the increase in the MS. So to do that, what system does is system prefers to break into domains. So let us say I am now breaking this fellow into two domains. This happens naturally. I'm not doing it. Spontaneously it happens. What is the meaning of that? See, what happens is if I actually do this into break into two domains, let us say equal area. So what is happening in one direction, the spins are all parallel, let us say. And also in this direction, the spins are all parallel within them. Don't worry about this line which is separating now for a minute. Assume that only half of it exists. In that case, the spins are all parallel here, spins are all parallel here. And so exchange is minimum. Exchange doesn't care where they have to be. So they only say that, okay, within the region, they are all parallel. Yes, fine. EK, you see, what happens to EK? EK is also minimum because I considered a hexagonal crystal in which it has a uniaxial anisotropy. So by definition, if the spins are parallel either to plus C, let us say this is C direction, or minus C, either parallel to C or anti-parallel to C, both are energetically same. So my EK is not changing. What happens to MS? MS, you see, now you see that there are, because of the orientation, the way in which this domain's orientation is there, you can have now individual poles north here and south and also south north. So you see that the field lines need not traverse in space so much so that they've closed the field lines, but they can always close that here itself. So the magnetostatic energy associated with that, which is nothing but half NdMs square, will actually reduce if we actually break into two domains. Okay, so that the system prefers to break into domains. But then you may say, okay, if I do it this way, can I now break into four domains so that the magnetostatic energy still decreases? Yes, you can. Yes, you can. But then can I break into 8 domains? You may not be. Why? Why? Because I am showing you a sharp line here which is separating out these two fellows, but it is not sharp line. This region in which the spins are all pointing up is called a domain, but the region which separates out one domain to another domain is called a domain wall. Okay, so the domain wall, if you zoom it now with a magnifying glass, I am actually looking at it. So this is one domain, this is another domain. So what happens is this switch from this to this cannot happen abruptly within a single spin. Why? Because that costs a lot of energy. See, this configuration will have an energy, let us say, minus 2js square. This configuration will have an energy 2js square. So, but if the total energy change, this plus 2js square, the total energy change would be, in fact, for a spin which has to flip, if you calculate it out, you will get to see that it's like 8js square, which is very, very large. So what spins prefer to do is they prefer to orient over a number of spins so that actually this total energy is divided by that n number through which this transition is taking from positive to negative. So that n is, of course, if it is as large as possible, then your flipping energy will be actually much smaller. Okay, so you prefer to have this to be very, very large width one direction to reduce the total energy in switching. But on the other hand, if it is going very large, then you see that more and more spins are now not parallel and also are not pointing along the easy axis of magnetization. So E exchange and EK will increase if this is spread over a number of spins, n tending to infinity, n tending to very large. They actually prefer that n tending to 0. So there is a trade-off. There is a trade-off between increase in exchange and anisotropic energy to the decrease in magnetostatic energy. Finally, the system will find some n which is compatible with these two scenarios. So that is where you will get a domain wall. So you will have a domain wall. And in fact, so coming back to the previous point, so whenever you create a domain wall, in fact, there is a small change, increase in energy of exchange and anisotropic energies. But then if this increase is less than the gain in magnetostatic energy, suppose you are able to decrease the magnetostatic energy much more than the increase in the exchange or anisotropic energy, then the system prefers to break into domain. Okay. But if this energy increase is equal or more than the gain in the decrease in magnetostatic energy, then system will not break into further domains, and then that decides the finite size of domains or finite size, how many domains you can have. So that is why what happens is, coming back to our iron nail story, the magnetization now has so many domains that each one of them are preferably, I mean, along the easy axis of magnetization. I told you that iron, there are 6 directions in which the spins can point. So there are domains in the 6 directions. So that the net magnetization average, if you see, it will be 0. So you don't feel that the magnetic, it is magnetic at room temperature. But it can be magnetized very easily. You take it and then just rub it with a bar magnet a few times, and then you are aligning these domains along the direction. Then suddenly you see that it becomes magnet. So there are domains already. But then since the domains can orient in different directions, the net magnetization is actually is 0 by itself, unless you do something like, you have to give a rubbing or stretching or whatever you do, you can actually, easily magnetize it. But TC is not the place where we are defining in that when you do not have any domains. In fact, when there is no orientation, sort of prefer, I mean, there is no interaction between the spins. Okay, so don't get confused with TC, right? Yeah. So you have ferromagnetic domains, and this can be pictured. I mean, there are a number of techniques. In fact, magneto-optical Kerr effect or bitter techniques, and many techniques people can actually visualize. This is not what I did about equations. Experimentally, we can look at domains, magnetic domains. Okay. In fact, we also take magneto-optical measurements in our laboratory. So we'll, I mean, so we can visualize domains also. Okay. So this is the how you can have. In fact, for iron, since the other 0, 1, 0 and 0, 1, 0 and 0, 1 bar 0 are also equally easy directions of magnetization, iron will have a very specific system where you can have domains in this fashion, which is called closure domain. Because here the magnetic field lines are completely closed loop. There is nothing emanating out. There are in fact no induced poles. In fact, in this case, this is an ideal system where the magnetostatic energy is 0. You don't really see any magnetostatic energy. Okay. So, okay, coming back to that's the basics of magnetism in a nutshell in few minutes. And coming back to the storage, we know that the storage is actually, we have seen that. I showed you that cost is decreasing, data storage density is increasing. People are, this capacity is doubling every 9 months, which I talked about already. And you can see that this is a IBM hard disk, okay, which occupied 15 to 24 inch diameter disk. People used to keep the storage disks in rooms, actually big halls. So from there you are talking about now gigabytes. In fact, this is also very old, 20 years old. So you have very low economics data storage also. The storage density is increasing and the cost is decreasing. So this is what happens. But then what happens to the size? When can I go on decreasing? Can I go on increasing the storage density? Okay, so that is the next question that we want to discuss. Any questions so far? Any volunteer?
Sir, participants are requested to raise their hands if at all any doubts.
Okay. Do you see anything?
Yes, sir.
Do you
Two
see any
participants are
doubts?
there, sir. Vijay Mandava, sir. I'll unmute her, sir.
Yeah, you basically ask them because
Yes, sir.
it should not be
Unmute
monologue.
her,
Yeah.
sir. Hello.
Yeah.
Vijay Madam?
Yes, yes, yes.
Yeah. Vijay Madam, are you there? Hello, madam. Yeah, please ask your doubt. You have raised your hand now. Any doubts from your side? Hello.
No, sir, by mistake it happened.
Okay. Okay.
And now that you are online, are you? I mean, following it? Is it okay?
Yes, sir. Yes, sir.
Huh?
It is very
Vijay, am I
actually.
audible?
Yes, sir.
Yes.
Audible, sir.
Yeah, yeah.
Yes, sir.
One
Audible.
one drawback with the digital teaching is that we don't get to see. Normally, I prefer to see into the faces and then not in usual teaching also, because the feedback is, as you know, all of us are teachers. Without feedback, teaching is the most difficult job. You don't know what wavelength you have to pitch in and whether is something is getting absorbed or everything is getting reflected. You don't know. We cannot calculate transmission coefficients and reflection coefficients, isn't it? It's very difficult. In fact, when we are doing online teaching, but that is the major drawback or complaint that I have. So unless participants, our students raise or ask something, we don't know what is happening, isn't it? I have to just to look at the slide and then talk to myself, isn't it? So any question?
So one, Dr. Joe. Yeah, ma'am. Proceed, ma'am.
Interesting and informative session, sir. Actually, I am also old student of HCU.
Yeah.
So I'm theoretical background. Quantum. I'm Chatterjee sir student, sir. Actually.
What's your name?
Vijay Lakshmi, sir.
Okay, fine. I think I was also in the doctoral committee member for you.
Yes, sir. Yes, sir.
Yeah, but probably you got a job and then left, right?
Yes, sir. Yes, sir.
Yeah. Okay.
But
Fine.
I'm trying to
Yeah.
continue, sir.
Yeah.
Sir.
Okay. Anyone else?
So Jyoti Ranjan Sahu, sir, is also there, sir. I'll unmute him.
Yeah.
Hello, sir.
Yes. Hello.
Good morning, sir.
Good morning.
Sir, actually, I have some doubts from basics.
Yeah.
That is, as we all know, that there is some spontaneous magnetization in the ferroenergetic compound, whereas there is no spontaneous magnetization in an antiferroenergetic compound. So,
Yeah.
so does this concept actually takes into account the entire substance or confined to a particular domain?
Yeah, very good question. In fact, spontaneous magnetization, when we talk about the subdomain magnetization. Okay. But because even if a ferromagnetic material, as I told you, the recent example of iron, okay, the net magnetization that you may not have, but then it will always have a spontaneous magnetization, isn't it? So within the domain, if there is a spontaneous magnetization, it is still in ordered state. Okay. But if you do a macroscopic measurement, okay, in an completely antiferromagnetic material, what happens is, unless you provide some quantization access by the field, okay, so that magnetization also, what happens is, the imbalance between these two domains will be so small that the net magnetization will be very, very small in the case of antiferromagnet. Okay. But in the case of ferromagnet, what happens is, since the magnetization is already in the domain, magnetization is already pointing along the easy axis, they can orient along the field very easily. So you see that there is a large increase in the magnetization immediately. But coming back to your question, yes, we talked about spontaneous magnetization definition. That is actually within the domain. So I should not be saying that there is no spontaneous magnetization in antiferromagnet. Antiferromagnets will also have a spontaneous magnetization, but the net magnetization is zero. Is that okay?
So in an antiferromagnet, there will be the spins lying antiparallel to each other in the same domain itself. Okay.
No. These two are separated by domain wall. It cannot be in the same, because I told you, right? If it is in the same, then the exchange and everything will collapse. It cannot. What happens is, like, let us say this is an antiferromagnet. Okay. So what happens is, the first two conditions have to satisfy, G exchange and GK. Okay. So it's not that every domain you can actually visualize. In fact, if you are studying antiferromagnet, you will consider it as two sublattices, and in each sublattice, you'll say that the spins are all ferromagnetically coupled. Okay.
Okay,
But then
okay.
these two sublattices are coupled anti-parallel or antiferromagnetically. So that is what you will model it. Okay.
Okay.
Yeah.
Sir, I have one more question. That is, what is the advantage of neutron diffraction over XRD in determining magnetic properties? Because as far
Yeah,
as
because
I know,
see,
for phase purity
but-
only we use XRD, and any additional things for which we may need neutron diffraction?
very good question. See, X-rays are insensitive to the magnetic moment. They don't really tell you anything about how the magnetic spins are oriented. Okay, they are parallel, anti-parallel, not oriented, that kind of information, because they don't interact with they only interact with the charge, electron. Okay, how the electrons are actually, but not with respect to the spin. But whereas neutron has a magnetic moment. So this magnetic moment of the neutron interacts with the magnetic moment of the electron. And thereby, if there is a net orientation, either in the ferromagnet or antiferromagnet, that information also you can determine. That's why we say that you can determine magnetic structure also, apart from the simple crystal structure. Okay, so that is the advantage of neutron diffraction.
Okay, thank you, sir.
Yeah, fine. Okay, so I was planning to complete the first part by this so that I can go to the second talk. Doesn't matter, because as long as things are fine, we'll try to see how much we can do. Okay, so what I'm talking about is, I am continuing now. Is it okay?
Sir,
Yeah.
will you please give 10 minutes break, sir?
No, fine. That's wonderful. I can. You let me know when I should come back, right? Yeah.
Yeah, now it is 11:38, sir.
Mm.
So let us start by 11:50 sharp.
Oh, okay, wonderful. Yeah. So
After 10 minutes.
I am connected only. I'm not switching off. Just
Yes, sir. Yes, sir.
we'll start at 11:50. Yeah.
Yes,
That's good.
sir. Yes, sir.
Wonderful.
Please.
Thank you. What decides and things like that. We are going to now discuss about what is the effect of size. Okay, because I said, right, nanomagnetism. Actually, there is nothing like nanomagnetism. What I'm talking about is magnetism in nanomaterials. Okay, but just to make more appealing, I put it as nanomagnetism. But you should understand that we are looking at magnetism in nanomaterials, right? So why size is coming into picture in nanomagnetism or in magnetism? So if you see that this is a picture, a view graph of coercive field versus diameter of a particle. You see that when you actually particle is a bigger diameter, okay, that means a larger particle like a micron size particle or a bulk particle, as I talked to you. That for the reason that I explained you, that magnetostatic energy should be minimized, or the total energy has to be minimized, the system prefers to break into domains. So that's why you will have a multi-domain. Okay, you will have not a single domain, but then you will have multi-domain. But then you are go on decreasing the particle size. What happens is there will be a stage where the particle size will reach a limit called a single domain limit. What I mean by that is, I explained you that to minimize the total energy, when you break this into domains, you will have a region called domain wall. And in the domain wall, I already explained you that exchange and magnetocrystalline energy will increase, because this is not the easy, this is not energetically favorable condition for these two fellows, because neither they are parallel nor they are pointing along a easy axis of magnetization. So, but this is inevitable. I cannot have a flip continue directly, because that will cost much more energy, right? So when I create a domain wall, I told you that there is an additional increase in energy, but as long as this increase in energy is less than the gain in magnetostatic energy, system breaks into domains. But then if you are decreasing the particle size so much so that a stage will occur where the increase in these fellows is actually less than the gain in magnetostatic energy. So then, I did not talk about magnetoelectric effect, magnetoelastic energy, which we'll ignore now. But basically, I'm talking about these three. So this gain in energy is the cost in increase in energy of making a domain wall will be more than the gain in the magnetostatic energy. Then the system cannot break into domains and becomes a single domain. Okay, no problem. Single domain is also fine. Only thing is the spins are all pointing along a single direction. That's okay. But now you decrease the energy further. At this point, what happens is, I want to draw your attention to this view graph here. In this single domain also, the spins can be either pointing up or down. Okay, all of them are parallel. But energetically, both the configurations are one and the same. Okay, but for whatever reason, either anisotropy or mostly anisotropic energy, these two fellows are separated out. So what happens is like a double well potential, where energetically both these potentials are the same. Let us say one is spin up and another one is spin down. Okay, I can actually, okay, I should have plotted this a little bigger scale. But anyway, so now what you see, these fellows are separated by a barrier, which is called anisotropic energy barrier. Okay, where K is the anisotropic constant, V is the volume of the particle. So what happens is, even though the energetically the spins have the same energy to point either parallel or anti-parallel to C axis, let us say, but then for whatever reason, if it gets stabilized in one configuration, it will remain so that it will not flip over. Okay, so that is what happens in the single domain limit. But if you are decreasing the volume particle size, what happens is, what you are doing, you are actually decreasing the volume. If V is decreasing because of the product in KV, this barrier height is decreasing. So barrier height keeps on decreasing. If the barrier height is keeps on decreasing, always thermal energy is at work. You know that you cannot ignore KBT, okay? Because theoreticians very conveniently take T is equal to 0 and then do all that calculation. But for experimentalists, for us, it is we cannot ignore temperature, right? Temperature is important characteristic. So KBT is the thermal energy. So what happens is, if KBT is equal to the KV, that is the anisotropic energy barrier, in that case, then what happens is the spins will have enough energy to flip from here to here, back and forth. So if they are going back and forth, then what happens is the magnetization becomes unstable, in the sense that your zeros, your spin up will become spin down will become zero, spin up. It can actually happen, without any additional this thing, because the thermal energy is giving that much energy, and the barrier height is now reduced so much that they can go back and forth. So in that process, what happens is that the spins are actually going back. So the magnetization is now like in unison. Their spins are still single domain, mind you. Okay, they're all pointing up, but then they can go continuously from up to down and up to down to up. So this region, this phenomenon is called super paramagnetism. So it's like a paramagnetism, but it's not like all the spins are all now in unison. They are all giant. The whole atom has one, like acts like a one spin. Okay, they're consisting of so many of these atomic dipoles. Okay, so these. So then what happens is, this becomes now you cannot store the information, because if you write 0, then that will become 1. If it become 1, then that becomes 0. So this becomes unstable. So if you are decreasing the particle size, every system will have a limit called super paramagnetic limit, beyond which you cannot store the information. But you have seen in the previous slides that we are in the process of decreasing the particle size, so that we can store and more information. Storage density can be increased, right? So the storage, so people don't want to give up, saying that there is a limit. So what they want to do is, now how do I tackle this problem? One way to address this is, can I increase the anisotropic energy K? Can I increase it? Okay. So of course, this is there are anisotropy means which anisotropy? There can be a shape anisotropy, there can be magnetocrystalline anisotropy. There are different forms which actually give you a resultant anisotropy to the system. So what happens is, you want to decrease the V volume, but then if you have a way of increasing K, still your KV can be greater than the KBT, thermal energy barrier, thermal energy, so that the barrier height is greater, and then you have a stable magnetization. So that is what people are working on. Okay, that is one of the aspects. So but is supermagnetism always bad? No, it is not always bad. For example, if you go to your cancer therapy treatment and things like that, hyperthermia, what they do is, they will actually inject magnetic nanoparticles, like suppose iron oxide nanoparticles, into the thing, and then by using applied magnetic field, they can drive these nanoparticles to the place where you have a tumor, and then at the point they can apply AC magnetic field, and these particles now will be randomly, like with respect to the field, they go on switching. So then they create local heating, and then the tumor can be destroyed. So superparamagnetic particles also have advantages. Okay, this switching back and forth is sometimes it is beneficial. You are able to increase, you are able to, that is much better than the chemotherapies and things like that. Okay, so people are actually using this magnetic hyperthermia in order to treat cancer and all that. Okay, some of the countries, I think in Germany it is already in place. In US probably they are waiting for the FDA approval. Okay, so that kind of things are all, they have additional advantages in terms of these things. So one, as I told you, for as far as storage of information is concerned, one thing is like, can we play with shape anisotropy? Can we increase the K so that it doesn't go to the super paramagnetic limit? Okay, so that is what one aspect people are looking at it. So GMR radiates I will talk about later. So this temperature now, okay, you talked about this temperature below which the magnetization is stable. That means in one of these configurations, either up or down, it is called, it's a ferromagnet state, but it's called a blocked state. Blocked state in the sense that the spin is now stable. The orientation is stable in one of the orientations. Unlike your bulk materials where you have a characteristic temperature called TC, Curie temperature, above which the material will lose this orientation and it becomes random, which is a paramagnetic state. In these systems, in the nanomaterials, there is another characteristic temperature called blocking temperature, which is actually given by dB. So what is blocking temperature? Blocking temperature is a temperature below which the magnetization is stable and will orient along a particular direction. But I mean, within the whole particle, in the whole single domain, the particles are all below the blocking temperature. The magnetization is now, is finite, but then is also, most important thing is spins are all stable. I mean, that means you can write the information, you can keep it in zeros and ones, whatever state they are. But above the blocking temperature, now what happens is the thermal energy is now equal to the anisotropic energy barrier. Now spins can go back and forth continuously. Still they are collinear, they are coupled. It's not like paramagnetic state. Okay, they are all coupled, but then what is happening is magnetization is going back and forth. So that kind of orientation, that is what happens blocking temperature. And of course, at very high temperatures, there is a TC, usual TC, where the orientation of the spins is also broken individual. They become individual spins and then becomes a paramagnetic state. Okay, so this temperature is TB, but this is a characteristic temperature. If you can push this TB to room temperature, you can actually use the material for your applications, for storage applications. Okay, so that the idea is, how do I know that? That means what I'm trying to say is, I want to actually extend the blocking temperature close to room temperature. So I can actually increase the anisotropy. So that is what people have done. So in these measurements, normally, how do we characterize the blocking temperature is, you do measurement in a protocol called, this is a typical measurement which we did in the laboratory, where magnetization is measured as a temperature, as a function of temperature. But magnetization is measured in two different ways using a protocol. The first method we call this is zero field cooled. What I mean by that is, initially when the sample is in the room temperature, at room temperature, let us say, you do not apply any field or make the field zero. Even if there is a trapped field or residual field, you have to make sure that the field is zero. Now you cool the system in the field, in the zero field to the lowest temperature that you want to measure. That's called zero field cooled. Okay. Now you apply the field that you are interested in, let us say 100 Oersted field, and measure magnetization while heating the sample. So you measure this. These white dots, basically what it gives is the magnetization measured while heating, having cooled the system in zero field. Okay, so this is the magnetization. Once you go to room temperature or 350 Kelvin, wherever you are, whatever measurement setup provides you, at that point, you do another measurement called field cooling. In this, what you do is let the field be on, but you are actually now, you can collect the magnetization while cooling the sample. This is called field cooling, because field has the experience or history of the magnetic field. In the previous case, when the first measurement was done, there is no history. There is no magnetic field history. In the second case, the field cooled case, the spins system or the magnetic movements have experienced the magnetic field and they know the history. And you see that because of that, you see that the magnetization actually will not drop like this. and it becomes like, in fact, it starts increasing slightly and then becomes attains whatever value that you have. And the bifurcation temperature, where there is actually this kind of a bifurcation between the zero field and field cooled measurements, gives you characteristic blocking temperature for nanomaterials. I have to be careful. You cannot, you see this kind of a system thing in many systems, when the systems have competing interactions and many things, but I am specifically talking about nanomaterials, where I'm considering this as a blocking temperature. So this is a characteristic temperature. Okay. Here what happens is, because of the local anisotropy, the magnetization actually has the spins are all randomly, different orientations. Now when you apply the field, only some spins which basically can be oriented along that will start orienting, and then finally the magnetization drops because of the above the blocking temperature, the spins now are actually randomly going back and forth, so the magnetization decreases. Okay, so blocking temperature depends on size, shape, and material and substrate. So they're depending on the film, depending on the system, you can tune blocking temperature. Okay, so you can actually do that. And so you can, one way I told you is that blocking temperature is actually given by, is also sensitive to the anisotropic energy. So you can actually change the anisotropy and increase the blocking temperature. So you can do that. And so nanomagnetism, what are the advantages? Advantages are, there are many sensors. People are talking about nanobiosensors. And at this point, I'll introduce in the second talk. Okay. People are actually looking at very high density media, ultra strong permanent magnets, and people want to use the spin of the material also, electron also, and for logic applications and all. I will spend this little later. Okay. So you see that there are grand challenges in magnetism. This is given by Sam Bader from Oregon National Laboratory. So in one of the papers, he has mentioned these are the challenges. And people are trying to address some of these challenges. Okay, in our laboratory also, we are trying to address some of them. So one aspect, again, I want to give one real application before we switch to the other topic, is that for, magnetocaloric effect, what it means? What it means is, we want to actually use magnetic principles to cool the materials for refrigeration purposes. Okay, why do we want to do that? Because normally in our gas household refrigerators are big refrigerators that are there for, for storing, for cooling ice creams or your chocolates or many things. Big godowns are there where then the materials are, of course, they will have refrigeration units, very big refrigeration units, apart from air conditioners that we use at home or refrigerators at home. So these are big refrigerator units are there. They all use a freon, which is basically gas. They use this gas, which, what is the principle? Principle is simply nothing but you compress the gas isothermally and then expand it adiabatically so that you get a cooling. Okay, so that is the simple principle, your Carnot kind of a thing. Isothermal compression followed by adiabatic expansion will give you a cooling. But what is the problem? The problem is some of these gases will, some of these materials will release gases which are environmentally not friendly. Okay, so these ozone depletion material gases, freon, gases, they tend to global warming, and India also has actually agreed into a treaty wherein we want to get rid of these kind of materials. These kind of technologies. So people want to switch to alternate technologies. One of the idea that is persisting, it's there, is that using magnetic refrigeration. What is the principle? Principle is use a magnetic material, okay, which is in a solid form, let us say. And you know that during the transition from ferromagnetic to paramagnetic, it doesn't undergo, usually doesn't undergo, actually state which will not change. Magnetic, it means if it is in a solid state, it will remain always solid state only. Sometimes, of course, there will be a structural transition. Okay, from one structure to another structure it can go, but most often magnetic transitions are not even associated with any structural transition. Structure also will not be the same, will be the same. And state, magnetics, the physical state, it is always a solid. Okay, unlike your conventional refrigerants where you have basically, you can have liquid gas, so that kind of a thing. So where you will sort of lose the gas and then it becomes, gas warming. These gases which go out into the environment will have problems. Whereas in the solid, there is nothing like, you don't lose any material. It is not really contaminating or polluting the environment. Okay, so you can use solid refrigerant, and for to take out that heat which is absorbed because of the change in the entropy or temperature change, you can use air or water for as a coolant, as a working fluid. Okay, you can use either air cooling or water cooling in order to cool your load that you want to cool. Okay, so this is the principle. I'll spend a little bit more time on that, but we want to also explore that how nanomaterials can be used. Can we use nanomaterials for this refrigeration? So that is the thing. So now, what is magnetic refrigeration? Magnetic refrigeration is what you do is, okay, you start with material without any application of any magnetic field, let us say. So spins are all randomly oriented, let us say. It may not be so bad. It can be that there are domains in which the domains are all oriented. That is also possible if it is a ferromagnetic state. Or if it is in a paramagnetic state, spins are all randomly oriented. So either one can be used. In fact, paramagnetic salts using to go to lowest temperature is again used, achieved. Okay, there is a Nobel Prize people got for this one. Okay, it's called it is not a new principle. Paramagnetic salts using for magnetic, for cooling is a old technology. But now I'll tell you what people are looking at is, initially people started using paramagnetic salts. Now you do not want to go to achieve the lowest temperature, but you want to operating temperature can be at close to room temperature, but you want to actually achieve refrigeration at that temperature. So it's not like going to millikelvin and all. That's not what we want. We want to go to the refrigeration efficiency. We want to increase. Okay, for that people are actually looking at ferromagnetic materials. Okay, and preferably if we can have nanomaterials, that's good. That why we'll see. So the principle is, initially at h is equal to 0, the spins are all random. So it has a large spin entropy, high entropy S1, and the temperature let it be T1. It has a spin disorder, okay, just about Tc or close to Tc. Now what you are doing is you are applying magnetic field and then isothermally magnetizing it. So that means, you see, when you apply a field, you are doing work on the system. Okay, thermodynamically, what you are doing is you are actually aligning the spins along the field direction. So that means you are applying the field, you are doing work on the system. If you are doing work on the system, usually, if you don't take the care of this isothermal magnetization kind of a thing, the temperature of the system will rise. Okay, because your work is being done on the system. So, but if the temperature increases, mind you, that because of the thermal energy, the spins will get randomized. So, but you want this magnetization to take place. So if you want to increase the magnetization, you have to make sure that the temperature doesn't rise. So that way, what you do is, that is why it is important to have isothermal magnetization. That means whatever temperature rise that has taken place in the material, that has to be dissipated, that has to be given to the surroundings. Somehow you have to make sure that temperature is actually in the heat, has to be given to the surroundings, so that temperature is maintained constant. Only then the magnetization can be increased. So that is why it is important to have an isothermal magnetization. So you connect to the surroundings, whatever heat has generated because of the work done on the spin system, that is dissipated to the surroundings, and the magnetization is increased. Once you do that, then what happens is, this is the state you will achieve. From here you have gone to this state where the spins are all oriented now. The spin order is now, spin disorder is decreased, so that the entropy, it will have a low entropy system. You see, from high entropy system, atoms, of course, they are vibrating around their mean positions, whatever is there given by the temperature, at whatever temperature you are in. But then, because of the change in entropy, now the temperature has, in fact, since the total entropy consists of two parts, one is the lattice entropy, another one is the spin entropy. Since the spin entropy has decreased, the temperature, now you see that you actually go to the lower temperature, T2. Okay, temperature is different, it has low entropy, and field is present. Okay, now what you do is, from here, this state, you want to demagnetize it adiabatically. That means you actually basically cut off the surrounding. Once you cut off the surroundings, what you want to do is, you want to now demagnetize. So switch off the field. If you switch off the field, spins will prefer to go back to this orientation. But in the process, what happens? The spin entropy is increasing. Spin entropy is increasing, but you are doing adiabatic demagnetization. So in the adiabatic process, what happens is, since you cut off the surroundings, temperature cannot change. Okay, so the total entropy has to remain constant. So what happens is, whatever increase the spin entropy is taking place, to that extent the lattice entropy decreases. okay, to keep the total entropy constant. And that lattice entropy is nothing but is decided by the temperature. So temperature has decreased now. So now you will go to a temperature lower than the initial starting temperature. Here I have put actually T1, maybe there is another one. Okay, this one, I should put it here. So what you see is the first step is spin entropy, spin disorder is there. You applied the temperature at a constant temperature, isothermal magnetization. Spin entropy has decreased. Now in this case, you see that S2 is greater than S1 or S1 is less than S2. Now this is your starting stage. Okay, so entropy temperature is T1, let us say. Now what you do is, from here you have gone to here demagnetized state, spin entropy has decreased, now it has gone to T2 a temperature. And so now this is an adiabatic process where the temperature is such that T1 is greater than T2. So you have decreased the temperature. In the process, what you have done is from here to here to here when you have gone, when you do adiabatic demagnetization, temperature has now decreased. So this becomes your starting point now. So you go on doing it again. So you can actually get refrigeration. You can actually cool it to lower and lower temperature. Okay. Okay. So in this process, you can actually, you have to only magnetize it and demagnetize it. If you do it repeatedly, you are able to cool it. Good, right? Why is it not being used? Why we still using freon based or gas based refrigeration units? The problem is this. Problem is, okay, actually in principle, this is demonstrated by a group in Ames laboratory. Schneider is the scientist who has actually demonstrated this by taking gadolinium as a magnetic element, okay, because this has a Tc close to 292 Kelvin. So what he did is he took 5 kgs of gadolinium and then he did this process back and forth. Okay, initially started with a temperature T. When you magnetize it, of course, magnetization in temperature increases, but you expel this heat so that this is done isothermally. So you come back to this. This is isothermal magnetization. Now adiabatically you demagnetize it. It becomes a T minus delta T. Then you can actually, whatever load is there, that load will be cooled because this heat is now taken from the load so that it comes back to this temperature. So this becomes your initial point, but in the process, the load has cooled down. Okay, so you have cooled the system. You repeat this, you can go on, cooling that load that you want. So this can be used. But what is the problem? Problem is, okay, see the cooling power in 1997 itself, it is actually demonstrated. Okay, but the problem is you want to use, for this to be active, he used 5 Tesla magnetic field. Okay, so 5 Tesla magnetic field to generate from an electromagnet it can, but it's very difficult because the I square R heating that is required to cool the magnets is enormous, and to generate 5 Tesla magnetic field you need pass a lot of current. Okay, and that current is probably the same as Telangana state current. Okay, so that is very, very expensive. So you cannot use that kind of electromagnet to generate. You can have 1.5 Tesla, maximum 2 Tesla magnetic field, okay, in a closed range, but not 5 Tesla magnetic field. But then what is alternative? Alternative is you have to use a superconducting magnet. But then superconducting magnets, you need liquid helium to cool them. So, and I told you that helium is very expensive. So what happens is, it's like, to save a penny, it's like you penny wise pound foolish. You are actually have to spend a lot of money and resources in order to use this. Okay, environmentally it may be friendly, but then you have to create liquid nitrogen, liquid helium, liquid nitrogen, pre-coolant, and then use this kind of a thing. So it is enormously expensive. Okay, so that is why this technology is still not in use. Okay, so what is the advantage? If we can come across a material which is superconducting close to liquid nitrogen temperature or at room temperature, then immediately this can be implemented. So that is one advantage. Okay, and also second thing is, nobody wants to keep 5 Tesla magnetic field in that home. For maybe industrial purposes you can still use it, but for domestic purposes, if you want to use, you cannot have such a large magnetic field because you know that there are health issues. Okay, when somebody has a pacemaker and things like that, they can interfere. So how much ever closed circuit you can have, there can always be a remnant field. So in the sense, it is not very practical to use such a large magnetic fields. to make the system work. So that is where people wants to use nanomaterials, because nanomaterials, what you can do is, if you can have a nanomaterial which can use magnetize and demagnetize at a smaller field, and also by changing the shape and size of the nanoparticles, you can also tune the operating temperature. You can in fact use them for magnetic refrigeration. So that is where people are actually looking at it, and a lot of work. So what you do is, as I told you, in super paramagnetic nanoparticles, the magnetization within the domain or within the particle, they are all oriented along a particular direction, but they are going back and forth continuously when there is no field, okay, along the easy axis of magnetization. So this is a disordered state. This is a high entropy state. But the moment you apply a small field, then that can provide a quantization axis. Now the spins can be pointing along one direction. So thereby the entropy is decreased, and you know that entropy and temperature are related. So thereby you can actually achieve cooling. So that is what people are actually looking at it and then trying to use magnetic nanoparticles. Okay, but still, I mean, people have to look at different things in order to get it. So this is one example I showed you. There are also, I think, oh, I missed out. That's what I was looking at. Okay. I think I pressed by mistake end button. Okay. Okay. So this is what happened? Okay. So change in entropy, you see, is actually related to the change in magnet. How do you actually laboratory you can measure? What you can do in the laboratory is entropy measurements also can be done from specific heat, but it is very, very cumbersome. It's not very easy. You know that you have to, use a certain amount of heat and then see how much temperature has raised in the material. But the material has to be kept in a holder, and then holder also will take some heat when you heat the heat. So you have to do just the pan and do the specific heat measurement, and then again put the material, do the background subtraction. So it is very cumbersome process. People can do it, but it is very different to measure the change in temperature delta T. So in fact, it is easy to measure, in fact, magnetization as a function of temperature at a given field, or as a function of field at a given temperature. In fact, what we do in a laboratory is we measure M versus H at a constant temperature, then do this at different temperatures so that you can actually compute dm by dt and delta H, and they integrate it out from 0 to H max, whatever is the maximum field. That gives you directly entropy change. So this is usually we use this in order to measure change in entropy. And once you do that, you qualify it that there is a sizable change in entropy, then one can actually go and do a more cumbersome specific heat measurements to measure the delta T. And if you can find a material which has a large delta T, then you are in the game. You can actually use it for magnetic refrigeration. Okay. So actually this field got burst. I mean, in another, when people have looked at this kind of material called gadolinium silicon germanium, and this is again Schneider group, which have published a paper here. What is the beauty of this sample is this material is that these materials have Tc, which is actually ferromagnetic to paramagnetic transition temperature. Around the same temperature, these fellows also have a structural transition. So that means you are not only tuning the magnetic entropy, but you are also tuning the lattice entropy, because there is a structural transition. So because of that, they see that a large change in the entropy. And this entropy, that is why this material is called giant magnetocaloric materials. Okay, giant caloromagnetic materials. So they have, you see that the entropy change can be of the order of 70 joules per kg Kelvin. So this is actually huge. This is very large. And cooling of several Kelvin. Using these materials, people have actually measured the change in temperature, and they see that even for a field of 2 Tesla, several degrees of Kelvin temperature change they have observed. Okay. So this is kind of even NIST group has published a paper in Nature in 2004 by having some iron dopants in these materials and things like that. So this is an ongoing work. Okay, it's not that I have a result and then can show you, but people are actually working in developing these materials. Nanomaterials again useful because if you can actually the efficiency of the system, the cooling efficiency of the system is not just the peak value, is not just defined by how much delta S you can get, but over what range. Okay, so delta Sm is a product of these two fellows, delta Sm, T dt. What is the temperature range over which you have a sizable change in entropy. This is called a full width at a half maximum. So this delta T over which this change in entropy is also important. In a usual system, ferromagnetic system, what happens is you will have a phase transition, a very sharp phase transition, so that the delta T is actually very, very small. Okay, but for efficiency, you need cooling power is given by this. So you need to have a larger entropy change, temperature range also. That's where people are looking at nanoparticles. So what the idea is, you can tune the size of the nanoparticles or shape of the nanoparticles, and thereby you can tune the TC, because there is a scaling between the TC and the size. So you can now increase the width of this range over which the entropy change can be seen by increasing the by having dispersion on the size of the particles. So normally we talk about monodispersed particles for certain applications, but for these kind of applications you don't really need monodispersed. You actually prefer to have a polydispersed materials. You would like to have a range over which you can change the entropy. Okay, so that is where this flexibility will not be there if you use a bulk sample, because bulk iron has a fixed TC, bulk nickel has a fixed TC, bulk gadolinium has a fixed TC. So you will not be able to play with the tunability of the TC. So whereas if you go to nano size, you will be able to change the TC, and thereby you can have a delta T. Okay, so that is the advantage of nanoparticles. Okay, so magnetic nanoparticles for magnetocaloric effect are actually used, and we have done some work and published a few papers. But at this point of time, our work actually is the blocking temperatures that we have seen are much lower than the room temperature. So they are not really useful for room temperature applications, but they can be used for a low temperature. Okay, if somebody wants to have a device or something to be cooled at low temperatures, or some sample to be cooled at low temperatures, this kind of refrigeration things can be achieved using magnetic nanoparticles. Nevertheless, there is a thrust, there is a work going towards that. Okay. Yeah, having shown you one example, I want to show you another example from our own work, where how do you actually tune the blocking temperature? How can actually change the shape and isotropy? I'll just give just a few examples some example. What we did is we have actually grown iron oxide nanoparticles. In fact, it's a composite system, gold iron oxide nanoparticles. Usually what happens is people will grow as like a spherical particles or a dumbbell particles. Okay, like I can have two blobs separated by one, around a nucleation. For example, gold. Let us say this is a darker one, gold is gold because of the higher electron density. If you see TEM picture, you see that this is a gold nanoparticle and this is basically iron oxide nanoparticles. So what we could do with a collaboration with another chemist from Brown University is that could grow iron oxide nanoparticles like petals. Okay, like you see that nature to physics, you could mimic nature in the laboratory. You could actually grow these iron oxide nanoparticles, and because of that, what you see is that this has this kind of a shape will have a different shape anisotropy in comparison to a usual spherical particle. So what we did is we took a usual spherical nanoparticles where you have like a core shell kind of a structure. Okay, and you can have a dumbbell kind of a structure where you have this is iron oxide, this is iron oxide, this is gold, like like a dumbbell. Or you can have an exotic shape like a flower nanoparticle. We call them as flowers because of this one. So they have like a petals grown around the nucleus, around this gold. So you can, by controlled chemistry, people have been able to do it these kind of exotic shapes. Okay, you can have different shapes of these nanoparticles. And what we showed from this work is that the blocking temperature, which I showed you earlier, is very sensitive to what is the shape of this nanoparticle. So you are able to tune that blocking temperature. Apart from, of course, that will tell you that what is the operating temperature for TC if you are looking at it, or you are able to, for storage density, suppose let us say that you are able to get more and more exotic shapes, you are able to shift the blocking temperature to close to room temperature so that the particles will not lose its magnetization or they will not become unstable. Okay, so this has advantages in various fields, so they can basically use it. So this kind of work is also something which people are doing. Nanomagnets are used as contrasting for in MRI for magnetic resonance imaging. Iron oxide particles coated with a suitable chemical can be injected into the bloodstream, and they can be mapped to different parts of the body by selecting particles of particular size then study specific parts of the body. So they are used for mapping, for imaging, and also both for diagnostic purposes as well as for therapeutic purposes. Basically, by applying, as I told you earlier, that by applying alternating field, you can actually make these particles randomly, very vigorously go follow the field, and then thereby they actually get heat locally and things like that. So nanomagnets are used in drug delivery. Okay, they can be coated with the drug particles, and then instead of, if you have a problem, then if you take a oral pill and all, it will affect the bloodstream, it will mix and then gets mixed with all the particles, all the healthy tissues also will get affected. But whereas if you want to have a targeted drug delivery, you want to only expose the tissue which is not healthy, okay, the tumor tissue, unaffecting the healthy tissue. So there again, magnetic nanoparticles are used so that they can be used for targeted drug delivery. So there are many things. Nanomagnets are used in healthy, in this one, in medicine, where what you do is cancer cells are more susceptible to high temperature than normal cells. So by increasing the temperature of tissue to more than 42 degrees, the cells could be selectively destroyed. So you can actually, targetively, you can select the tumor cells and then detect. So these are some of the applications and uses across the discipline, not just storage, not just in refrigeration, not only in targeted drug delivery, non-cancer therapy, and many other fields. So nanomagnets are used in various fields. Okay, so this basically concludes my first part of the talk. Second part, I actually promised something else, which I will take up in few minutes. If I have participants have any questions on this, okay, I will ask them to raise them now before I go to the second part. Okay, any questions? Yeah, any questions from the participants? No? Are you there? Participants are there? Hello? Hello? Somebody is asking, unmute. Jyoti Ranjan Sahu. Vijay Kumar is there? Okay, I think someone has to unmute you. Till then, I'll proceed with the second part of the talk. Okay, so yeah. You can type your question in the chat box also, okay, so that I can look at it, right? So I'm talking about little bit on spintronics. Okay, this is another area where we are working, and some of this work which has come out is published in these papers. I will not be able to, I think I have less than half an hour time, or probably half an hour time, 12:34. So I may have 40 minutes time. Let me see how much I can do that. But then I'll try to focus at least on these two red colored publications, okay, from results which have come out of these two publications. And yeah, all of you know that University of Hyderabad last year became Institute of Eminence. So this is our logo there. So coming back to this, I'll give brief introduction to spintronics, and then these materials which I'm talking about, Hössler alloys, what are these materials and why they are important, and some results from our work. Okay, so that is what I am presenting. Okay, yeah. So actually, how do I get rid of this? Yeah. Okay. So introductions is basically, okay, we know that electrons have a charge, and we use in devices, okay, in diodes, transistors, or many things, use the charge of the electron in electronics, right? Basically, that is what we have been doing it for all devices and sensors. But we know that electrons, apart from charge, also has a spin. So people are looking at how do we take care of the spin. and use it for transport. Okay, so that is the idea. Okay, so this using spin of the electron apart from the charge of the electron for transport properties, so that I can actually selectively choose for transport. So that kind of a thing is nothing but is a spintronics. So you know that for electronics we use a diode and transistors, but now what we are looking is for magnetic recording and permanent magnets. We want to use the control of the spin by electric field using spin orbit coupling, or control of electric current by magnetic field. So we want to use another tunability apart from simple electric field to drive the electrons. So we want to use the spin. So I want to control the spin either by electric field or magnetic field. Okay, so I want to actually control the transport of this electrons through spin. Okay, so that I can use more devices. So that is what is actually all about spintronics. So integration of magnetics with electronics to develop multifunctional devices, because I want to now tunability can be increased, not just the electric field, but I want to use magnetic field also as a and temperature, of course, for controlling the device. So spin polarized charge carriers transported through the non-magnetic material. So there are, I'll give you 2 examples for these kind of devices. One is a spin valve. Valve is nothing but, like you have a tap at home, you have a valve to control the flow of water, right? You can switch off or switch on, so water will flow or water will flow. So similarly, I want to use the valve such that based on the spin, I can control the flow of the electrons. How do I do that? So for that, what I will do is I will actually, the device structure is like this. So I will have a ferromagnet in which the spins are all pointing along one direction, let us say. Another ferromagnet in that again spins are all pointing. But this ferromagnet is coupled with an antiferromagnetic layer. So this is called pinned layer. Okay, so this is pinned layer. And this ferromagnet is separated with this respect to this ferromagnet through a non-magnetic spacer. So you have a spacer. So this is a free layer, ferromagnetic layer. There is a spacer. There is another ferromagnet, but this ferromagnet is not a free layer, but it is coupled with an antiferromagnet. So this fellow, magnetization is now coupled with this fellow. So what my interest is, I can, let us say this ferromagnetic layer, the magnetization is pointing up. Okay. And this is pinned with this antiferromagnetic layer so that this fellow is pointing up. How I do it is left to me, but I am saying that, okay, there is an antiferromagnet which basically holds this fellow so that it doesn't flip. It is parallel. Let's say plus Z direction. Whereas this fellow ferromagnetic, this magnetization in this ferromagnetic layer, by applying magnetic field or electric field, I can now flip this either up or down. Okay, without affecting this fellow, because there is a spacer layer which is separating these two fellows. That is my geometry, that is my construction. So that means I can have a situation in which the magnetizations in these two ferromagnetic layers can be either parallel, okay, or by switching this alone, I make them anti-parallel. So that is my job, task. So I can make them parallel or anti-parallel. Okay. And I will show you that if both of them are parallel, then the electrons can go through this non-magnetic layer into this without any hindrance, without any difficulty. The scattering is not there. It is actually, it is possible. So that means how it happens, I will explain in a few minutes, but believe me now. What I'm saying is, if these two ferromagnetic layers, if the spins are parallel, magnetizations are parallel, the electrons can actually go through this without much hindrance. Okay, there is maybe some hindrance because of some scattering or whatever, but there is no additional scattering. Okay, so that will give rise to a low resistance state. That means electrons can actually go. This is like on. I am basically opening the tap, so water can flow. Similarly, here this valve such that it is open, valve is open, so these fellows can actually, electrons can pass through. On the other hand, if this free layer magnetization is anti-parallel to this fellow, then these electrons now cannot go through. So this is like a closing valve. So this valve is working based on the spin state of these electrons, whether they are parallel or anti-parallel. So that kind of a gives me a device. It's called a spin valve. Okay, so now you see that earlier I could have controlled the flow of these charge carriers based on whatever, temperature, defects, and whatever, that kind of a scattering mechanisms that are involved. But now additional control I have a control based on the spin of the electron, which I am, at my will, I am changing this up and down by the application of magnetic field or through spin orbit complete by electric field without affecting this flow. So I can actually make this flow of electrons across this non-magnetic spacer either on or off. So this is basically this non-magnetic layer normally is a metal. Okay, so that the electrons are actually passing through without having additional scattering hindrance. Okay, so this is for metallic system. I can have this kind of a architecture. On the other hand, I can also have another architecture which is called magnetic tunnel junctions, wherein I have two ferromagnetic layers separated by an insulating layer, but insulating layer is normally an oxide layer, which is very thin layer, because I am not looking at a transport, I am looking at a ballast, I am looking at the tunneling current, I am not looking at the ballastic current. Okay, basically current has to pass through, tunnel through, but again this time this tunneling current will be decided by whether these two ferromagnetic layers are parallel or anti-parallel. How I can do? I can maybe, if I want, I can put on a non-magnetic layer. Doesn't matter. But this tunneling current will be different if these two spins are in the spin. The magnetizations in these two layers is either parallel or anti-parallel. So it acts like this valve only. Okay, but this time it's not like electrons are actually flowing through this, but it's tunneling through this barrier. Okay, so these will give rise to opportunities to make new devices which work on the principle of I am using the word polarization now. That means the orientation of the spin. I am calling this as polarization. So depending on the polarization of the spin, this device will work, either spin valve or MTJ. Okay. So efficiency of spin transport. I am looking at now spin transport on this due to these structures demands that I would like to have 100% spin polarization. So what I am trying to say is, in a usual material, actually I will explain in this graph. So what is spin polarization and what happens in usual materials? That's what we are looking at. So normally, I'm giving you a simple paramagnet here. Okay, don't worry about these definitions now. Look at this material. This is a magnetism. There are two ways of understanding magnetism. One is a localized picture. Another one is a band picture or itinerant picture. I'm giving you a band picture. Some of you might have come across this. What I am plotting here is now density of states as a function of energy, which we have shown earlier. Okay. So what you see is in a normal material, in a normal metal, paramagnetic metal, such as aluminium, what you see is that the electrons are completely full up to the Fermi energy, but there are equal number of spin up and spin down electrons. Okay. So the number of electrons spin up is equal to the number of electrons spin down. Okay. They are full up to the Fermi energy. But the magnetization in general in the itinerant picture is defined as magnetization is nothing but mu b, that is the magnetic moment associated with an unpaired electron, multiplied by the difference in the population between spin up and spin down. So mu b into n spin up minus n spin down gives me the magnetization at any given temperature for a general material. So in this case, if you see, in the absence of any magnetic field, since the number of spin up and spin down electrons are the same, so the net magnetization is 0. So this fellow will not have any magnetization at 0 field. That's what happens in a paramagnetic system. But if you apply a magnetic field now, what happens is, let us say apply the magnetic field parallel to the spin up state. Okay. So then what happens? There is a Zeeman energy associated with that. What is the Zeeman energy? My Zeeman energy is minus mu dot B. B is the magnetic field strength. Okay. So Zeeman energy ensures that the total energy has to be less, decrease. Okay. So in the given magnetic field, so the population of the spin up states will go up. Okay. So there will be more number of Okay, in this example, what I showed you is the magnetization is pointing along spin down. Okay, let us say it is, I could have done in any way. So let us say spin magnetization is pointing along spin down arrow. So now what happens is some of these fellows, spin up fellows, will flip over and then occupy the states in the spin downs to minimize the total energy. Okay, so that, of course, how many will change? That is decided by given by temperature and the field that you apply and things like that. If you go to very, very low temperatures, then more number of spins will be in this direction. Or you apply very large field, the so-called saturation, then more number of spin down states are populated. So then there is a net magnetization because the population density, population is not the same between spin up and spin down. So the population difference multiplied by the mu b gives you the magnetization. So magnetization is now will grow. Okay, magnetization will increase. In a paramagnetic system also same thing happens. But in a ferromagnetic system such as iron or cobalt, what happens is whatever field was doing in this case is done by the exchange field or internal field, or if you are looking at a very classical way of understanding things, then it is your Weiss molecular field. Okay, so this is nothing but because of the coupling, it is like this, chicken and egg. So the coupling is responsible for the magnetic field, internal field, or internal field is responsible for the coupling. So because of that, certain orientation is more preferred than that, the other one. So there is a net magnetization, which we discussed as a spontaneous magnetization. So in a usual ferromagnetic state, you see that there are always a density of states for one certain orientation are preferred than the other spontaneously without application of magnetic field, so that there is a net magnetization. So we can define something called spin polarization. What is spin polarization? Spin polarization is the population or the density of states at the Fermi energy with spin up minus their population density of states of spin down at the Fermi energy divided by the total density of states for both spin up and spin down. So this is a spin polarization. So in a usual material, in a usual ferromagnetic material, spin polarization will be there, but it is like a few percentage. It can be 5%, 10%, it can be 15%, depending on the spin pole material that you are looking. It is specific to a given material. Okay. But then there are certain class of materials which are called half metals. What is half metal? What is a metal? Metal is the one where you do not, at the Fermi energy there is no band gap between the spin up and spin down band. Between the valency and conduction band, so that the electrons are available for freely for transport. So you apply some voltage, then electrons will sort of will experience, of course, scattering with the iron cores or with the ion cores or with the electrons, other electrons, but then they are available for flow. So then the resistance will decrease. It increases. Resistance actually in this case, what happens is because of the scattering, of course, the resistance will increase because more number of electrons will remain the same, but the scattering increases. So at any given temperature, let us say at room temperature, the resistivity is actually very, very small. Okay, because more number of charge carriers are available, more number of electrons are available for flow. So electrons can flow easily. Okay, so that is what happens in a metal. On the other hand, in insulator, there is a large band gap between the valency and conduction band, and there are no charge carriers available for conduction in the conduction band. So you have a large resistance in an insulator. But in a semiconductor, what happens? There is a small gap between the spin up valency and conduction band, and so if you increase the temperature, then what happens is more number of valency band will gain that energy and go to the conduction band and are available for conduction. So that now with increase in the temperature, the resistivity decreases because more number of charge carriers are available. Even though there is a scattering, but then it is because of the increase in the number of charge carriers, population of the charge carriers, more number of electrons are available and resistivity decreases or resistance decreases with increase in temperature. So those are semiconductors, right? But in these class of materials we are talking about, where for one spin channel, it is completely full. The density of states is completely full up to the Fermi energy. Okay, so for let us say spin up, doesn't matter, but spin up, let us say. So as far as the spin-up carrier is concerned, the electrons with spin-up charge carrier are concerned, they act like metal. So that means there is no gap, or there is no spin gap. Okay, there is no band gap rather for this kind of materials. Whereas for the spin down channel, because of the hybridization that the material, why it happens like that, I've time depending on the time, I'll explain you. But you can take now that there are certain materials in which there is a for spin down channel, there is a spin band gap at the Fermi energy. That means these electrons are not available for conduction at a given temperature. Okay, so for these fellows, they act like semiconductors or insulators, depending on, of course, the strength of the band gap. But whereas for the other spin-up channel, these electrons can actually participate in conduction without there's no gap, so they'll act like a metal. So that is why these materials are called half metal. Half metal means for one kind of a charge carrier, they act like a metal. For another kind of a charge carrier, they act like a semiconductor or insulator. So if you calculate spin polarization for these materials, you see that this fellow will have some finite value because spin up has full up to the Fermi energy, whereas spin down, there's no charge carriers, density of states is empty at the Fermi energy. So this is 0. Whereas again, this is 0. So this n up by n up, basically 1, that is nothing but 100%. So these materials will have 100% spin polarization. So that is very good. Why? If we go back to your previous slide, see, if we have a 100% spin polarization material FM, and so is here, so same material mostly we take. So what happens is, either I can make them all of them parallel or all of them anti-parallel. Because in this material, at the Fermi energy, only one kind of spin channel is full. That means only those electrons are available for transport. So either the electrons are completely parallel to the state or anti-parallel to the state. So the efficiency of the material, the device will be enormous. It will be very, very good. Okay. So same is the case with here, magnetotangential. So people are actually looking for these kind of materials which will have 100% spin polarization at Fermi energy. Okay. So these are half metals. So these are very, very useful. I do not know whether I'll have time, but I'll just introduce you something called magnetoresistance, where apart from when you apply a magnetic field, then what happens is the electrons, that when their actual electrons are traveling, they will have a drift velocity finally, because they will undergo a lot of collisions, even though electric field is trying to accelerate. But because of the collisions, they will have a finite resistance, and finally they will attain a drift velocity and then go. Right? Normally that is what happens. But over and above the electric field, you apply a magnetic field. Now these electrons will actually travel in a circular path. So that means they are actually experiencing more and more collisions, because they are not really going in a straight line path. So that there is a more resistance, and that resistance that is present because of the additional collisions or less in traveling path. Actually, these fellows will have a Lorentz force. Okay, both electric and magnetic fields. QV, EV plus what you Q into V cross B. Okay, you will have an apart from the electric field, you will also have Q into V cross B. Q into V cross B is nothing but the Lorentz force. Okay, that is coming because of the magnetic field. So you see that increase in the resistance applied magnetic field, that is called magnetoresistance. So that is usually there. Okay, but what Fert and that I'll explain. But what Fert and Grunberg, what they have seen is, apart from this is the Nobel Prize. The first talk I showed these two gentlemen, right? They have seen that if you in antiferromagnetically coupled, in antiferromagnetically coupled, like this kind of a material, okay, this is antiferromagnetic coupled. So you have two iron layers separated by chromium. This is a spacer layer. You see that this is antiferromagnetic coupled. In this layer, what happens is they have seen that there is a large magnetoresistance. Okay, resistance change occurs when the relative orientation of the magnetic moments change. Okay, from in the ferromagnetic layer, the resistance is small, and again when they are coupled ferromagnetically, of course in the other direction, the resistance is small. But then when they are coupled antiferroparallelly, they have seen that the magnetization increases a large change. In fact, this is called giant magnetoresistance. This is what actually Albert Fert and Peter Grunberg did this in iron chromium multi-layers. They have seen that such a thing can be realized. This is coming because that these magnetic layers are now coupled anti-parallelly. So the magnetoresistance can be very large. So this is very, very interesting. And this can be realized using in spin valve. So people have done, like nickel iron and nickel iron. These are two ferromagnetic layers coupled, separated by a copper antiferromagnetic spacer layer. And one of the ferromagnetic layer is coupled with an antiferromagnet, iron manganese. This is an antiferromagnet. So you can couple this fellow, and this can be tuned parallelly or anti-parallel to with respect to this. It will by just applying magnetic field, so that you can actually make them parallel or anti-parallel, so that the resistance can change, so that the flow of electrons can change, and you can actually make it as a spin valve. So this is a kind of a structure you can do. So this is in fact used. So you see that when you are actually reading device, when you actually suppose you have bits where data is stored, zeros and ones and ones and zeros and one, you take a read head which works on the principle of GMR. What it does is it will see whether there is a large resistance or small resistance. If there is a large resistance, you know that if you have already polarized this read head, okay, along one direction, then it will measure the other fellow is parallel or anti-parallel. If it is parallel, then you can call this as, let us say, ones, let us say, and if it's anti-parallel, zeros. So you go on reading this information by just measuring the resistance. If you go on by measuring the resistance, you can actually encode the information into zeros and ones, and then from there you will be able to read the information. Okay, so that is why it is actually so beautiful that your read head sensors all work on the principle of GMR. Okay, so this is acts like a sensor. This acts like a device which basically measure whether the given sample, given bit is oriented parallel or anti-parallel to your bit. Okay, so that is the thing. And for ferromagnetic metals, the electrons. Okay, so why is that? They will experience resistance. I is explained in this picture here. So let us say this is a ferromagnet and this is a ferromagnet. This is a non-magnetic layer, okay, like a copper. What I am doing here is, let us assume that in both these orientations, now the spins are parallel. Of course, each one of them, mind you, each one of them have a spin up and spin down. But in this case, you see that this is a spin down channel, let us say, when I apply some voltage, can go from this position to this non-magnetic spacer layer, and then go to this position again, because there is a spin down channel available at the Fermi energy. So this will constitute a low resistance state. So electrons can go from here to here, then go here. So not much of a problem. So this is a low resistance on position, let us say. On the other hand, when you go to a high resistance mode, what is happening is, you see this carefully. You see that in this case, the spin is, let us say, is retained in this orientation only. But whereas in the other case, the spin is flipped now in comparison to this. You see, spin down channel has become now spin up, and spin down has become spin up. So this fellow magnetization is now switched from this orientation. Here, both of them were parallel. Here, they are anti-parallel. This is spin down, this is spin up. Right. What happens is, when you apply voltage, this electron with spin down can go here, no problem, no issue, because this is a non-magnetic layer. Both are spin up and spin out are equally populated, and they are available at Fermi level. So it can go, no issues. But then it cannot go here because there is no spin down channel available here. Okay, there is a spin up channel, and without undergoing any spin flip, my electron is going with spin down orientation, polarization. And since there are no spin down electrons available at this, see this here, there is a gap at the Fermi energy, whereas this fellow is full, but then with spin up. So I will not be able to transmit this. So this will experience a very high resistance. So you can see that how we can understand this GMR concept using this cartoon. Okay, so to start with, if I have only one kind of a spin up or spin down in these two electrodes that I'm talking about, then I can control my flow of charge or flow of electrons with 100% efficiency. I'll be able to actually make it a very good device. Okay, so that is why there is an urgent requirement. There is a strong requirement of having only one kind of a spin channel available at the Fermi energy, or for half metals. People are actually looking at half metals. Okay, so that is the same thing in the tunnel magnetoresistance also. Depending on the orientation, if they are parallel, then it will give a low resistance for tunneling current, and if they are anti-parallel, they will have a large resistance for tunnel current. And magnetoresistance ratio is now resistance when they are anti-parallel minus parallel by resistance into parallel. So this will give you how much of the efficiency of this magnetoresistance. Okay, so that can be used for magnetic tunnel junctions. So I'll actually use that. How much time I have? It's 1 now. I was told that I can take up to 1:15, so probably another 10 minutes I'll take and then stop it and then take your questions if you have any questions. Okay. Since my title, it gives me Huesler alloys, at least I have to introduce what are the Huesler alloys. If we don't get time to discuss my results, that's fine. Okay, Huesler alloys for the first time discovered by Fritz Huesler in 1903. What are these materials? These materials, you see, usually ferromagnetic materials, when we consider in elements, how many are there in the periodic table? Elemental, if you see, only 5 are there: iron, cobalt, nickel, gadolinium, and dysprosium. There are 5 elements. And prior to this work, people have made other ferrimagnetic or antiferromagnets or ferromagnetic compounds having at least one of the constituents of ferromagnetic elements. Okay, either iron compounds, cobalt compounds, nickel compounds. So they also can exhibit ferromagnetism. That's fine, no problem. But for the first time in 1903, Huesler showed that starting with non-magnetic elements, okay, like copper, manganese, and aluminum, he made this compound Cu2MnAl. None of them are ferromagnets. Okay, but then this compound, this alloy, is found to be ferromagnetic, which has a room temperature above Tc above room temperature and has also large magnetization. Because this opened up gates to many more materials. Okay, so you don't need to have a constituent element to be ferromagnetic, to make a ferromagnetic material. So that is why this class of materials are named after this scientist, Huesler. Okay, so these materials are called Huesler materials, Huesler alloys. Okay, so then, okay, people were looking at it and then people wanted to see that, okay, what is the use, what are the, they can be used for shape memory, they can be used for refrigeration and many things. But then later on, in 1983, it's just a few, 30-40 years old, that De Groot, who is another scientist, he did theoretical calculations and he showed that these alloys can be half metallic. So that's where the real interest came. Then people started looking at these materials because unlike your simple iron, cobalt, and these kind of ferromagnetic elements, the advantage with these materials is this: not only ferromagnet, but they are also half metallic. That means one of the spin channel, it is completely full up to the Fermi energy, another spin channel has a gap at the Fermi energy. So you can in fact use them for devices in spin valves or tunnel magnetic junctions. So these materials will have applications in spintronic devices. So that is the main interest people have. Okay, so there is the growth, the interest has grown. Now we'll see a little bit more. So then advantage and disadvantage, there are a lot of advantages of these spintronic devices. In fact, any of you who are interested in trying to understand more and read more, I suggest this book. This is a very good book. Huesler alloy properties, growth and applications, Springer Publications. I have taken this view graph from that book. So wherein you can use these materials for hard disk device, storage devices, sensors, MRAMs, magnetic random access memories, in fact, racetrack memories, and many things. Okay, they are useful. The characteristics are like this. Sorry. You can actually replace some of these Huesler compounds. I'll talk about. They will exhibit different types of crystalline orders. I'll show you that in a minute. And they have a Curie temperatures above room temperatures, and they have lattice matching with respect to major substrates, so you can grow thin films. That's a very useful thing. And they will have low coercivity and large activation. So they can be switched very easily. Okay, low coercivity means magnetization can be switched very easily. So they have a lot of advantages of these material, these kind of class of materials. Okay, so we'll see that. So if you see the periodic table, you see generally these kind of materials have something called X2YZ. I showed you that Cu2MnAl in the first slide. So if you have this kind of a structure, these are called full Huesler alloy. Okay, so originally was prepared by Huesler himself. Okay, so these are X2YZ structure. And what are XYZ? X and Y are transition metals. Any transition element, you can actually see that such a large choice you have. And Z is in general a p block element. Okay, so this is the element that you can take. So with these elements, people have made hundreds of alloys. In fact, thousands predicted, and many are made actually. And also, it's not just a peculiar one structure. There are other structures also. Like for example, instead of X2YZ, you can also have XYZ. That means one formula unit in the X is missing in one of these things, where you have equal X, Y, and Z. These are called half Huesler alloy. So there are different class of materials. In fact, there are 4 classes. I will not go into too many details, but you can have different, depending on your choice. You can select different elements in the periodic table and make a stoichiometric material, and then get into these Huesler alloy. And you see that most of them will have TC above room temperature, large magnetization, and also very good spin polarized materials. Okay, so that is what is the interest. In general, if they are, of course, they are crystalline, but you can make them crystalline. But then if there is something called ordered, fully ordered, that means each atomic position given by, for example, they consist of a unit. For example, I'm talking about this full Huesler alloy, in which there are 4 unit cells interpenetrating FCC sublattices with the position of the atoms for these XYZ such that 0, 0, 0, half, 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 1, 4, 1, 4, 1, 4, and 3 by 4, 3 by 4, 3 by 4. So these are the positions for X. The first 2 are for X, then this is for Y, and then this is for Z. So if these atoms occupy their respective positions, okay, completely, without any exchange between these atoms, then it's called fully ordered structure, which will have L2-1 structure, and this is completely ordered. Okay, but then you can have exchange of Y and Z between Y and Z. So that means, okay, there is an underlying crystal structure, no doubt, but some of these positions occupied by Y are occupied by Z, and some of the positions occupied by Z are occupied by Y. If such a thing happens, then that is called B2 disorder. Okay, so it's not completely ordered. There is an underlying crystal structure, no doubt, but then the positional disorder is there. Some of these positions are not completely occupied by the respective atoms, but then they are occupied by other atoms. Okay, so if such a thing is called, this is called B2 disorder is there. And then you can also have A2 disorder, wherein X and Z and X and Y, between X and Z there is an intermixing, and X and Y there is an intermixing. So such a thing is called A2 disorder. If it's completely random, everything is occupied this one, then it's basically amorphous material. So you can also have amorphous material where you can have completely random occupation. But then people are looking, as I told you, in the periodic table, there are a lot of transition elements. So you can get started with something and then go on making different kinds of alloys. But there is a lot of interest based on cobalt-based Huesler alloys. So wherein why there is interest is because they have a large TC and large magnetization and good spin polarization. So people are looking at these kind of materials. So we also started looking at this class of material called CO2 FeSi. So where you have cobalt 2, iron, silicon, and for a various we have a lot of interest. We want to understand actually the magnetism in this material, the transport in this material, and we also want to understand magnetism switching in this material. So we wanted to understand a lot of things so that one can actually plan for a good spin valve or MTJ kind of a devices and things like that. Okay, so that was our interest. So we grew these films using sputtering, high vacuum sputtering, and then we try to understand the magnetism and transport in these materials. Okay, that's what so these materials are actually predicted to be having such a large 6 Bohr magnetic moment per formula unit, and they are also supposed to have a large TC. Okay, and these materials actually expect to show a typical behavior of Slater polling, wherein the total spin moment is with respect to the number of valency electrons. If you look at it, there is a formula which is given for, full Husserl alloys. This is given by ZT. That means the total number of electrons minus 24. Okay. And for half Husserl alloys, it comes out to be ZT minus 18. So this is expected, and you see that large number of alloys will fall into this kind of a material. So I showed you a typical pictures, but it is actually is given by in this book, in this paper. So you will see that many number of them are actually follow this. This is called Slater polling curve. They will follow. And the magnetization in this principle, in these materials are also can be understood in terms of hybridization. What you see is that suppose if we consider cobalt atoms, these initially cobalt atoms, CO2 FeSi, if you see, initially cobalt atoms will form bonding and anti-bonding states by forming this. And then these cobalt atoms, the E2G orbitals of cobalt atoms can couple with each EG orbitals of another cobalt atom, resulting in the bonding and anti-bonding states. And then these bonding states again will couple with respect to the iron bonding states, so that you will have again another hybridization takes place. But whereas these anti-bonding states, because they cannot couple with respect to the iron bonding states, thereby there is a band gap. So for one of the spin channel, on spin down channel, there is a spin gap, whereas for the spin up channel there is no spin gap. So one can understand how half metallicity is coming in these kind of systems. The more details you can see this paper, you can see that. So we actually try to deposit these films with the different orders, because our idea was to see that how the disorder is changing the magnetic and transport properties, how the thickness is affecting this one. So we try to grow these films with the different disorders by tuning, by varying the substrate temperature. We are actually, when you are depositing the films on substrate, we could controllably vary the substrate temperature. For a given deposition, we kept the substrate temperature constant. So we deposited that, and then at different substrate temperatures, so that we can actually vary the order in this system. And then we carried out a very detailed transport, magnetization, magnetoresistance, ferromagnetic resonance, magneto-optical Kerr effect. So variety of experimental techniques we have used in order to characterize and study and understand the magnetic properties in these systems. So I think I'm actually run out of the time, but I can show you that we use various parameters and all. Of course, structural characterization is carried, magnetization characterization is carried out. Try to understand the magnetism in these materials using spin wave theories predicted for thermal demagnetization, and try to understand, get the magnetization stiffness constant and the other parameters from this. And we actually try to pinpoint that what are all the different contributions for magnetization and transport. I'll just show this slide and then probably wind up, where I'd say that how the electron transport, in general are affected. There are different mechanisms, resistivity mechanisms, like electrons can get scattered because of the impurities. The potential experienced by the impurities is different, so there will be a scattering because of the electron impurity scattering, which is mostly temperature independent. So we call this as a rho naught. If to get this idea estimate of that, one should go to the very lowest low temperatures. Okay, as low as T tending to 0, so then you can get what is the rho naught. Okay, the estimation in terms of electron impurity. And electron also can get scattered because of electron interaction, which goes as T square. Okay, and electrons can get scattered, that because of the lattice vibration, which goes as T to the power 5 at very low temperatures, or T cube at intermediate temperatures. And electrons can get scattered also because of the spin wave excitations, which are called electron magnon scattering. So you can get these different scatterings, and then resistivity can increase. But if you have a disordered material or amorphous materials, then you can, apart from these kind of contributions, you can have some contributions which will have a negative temperature coefficient of resistance, which are called also called quantum corrections to resistivity, which are called weak localization or enhanced electron interaction, which will have this kind of temperature dependence. So which will give rise to an increase in the resistivity at low temperatures. Okay, this is a metallic behavior, but this looks like a semiconducting behavior, which is not true. This is a CO2 TSI. This is coming purely because of the disorder that's present in the material. So what we did is we did a very detailed transport measurements, and then try to find out what are all the responsible mechanisms and what is the temperature range, so that we can understand these things. And we also did another important aspect called Hall effect, anomalous Hall effect. So in the ferromagnetic materials, apart from the usual Hall effect which see in semiconductor pictures, materials will have an additional contribution to the resistivity or Hall effect because of the spontaneous magnetization. So we have seen that, and then we try to understand and estimate what is the contribution of that. And our final goal was to see what is the relation between this anomalous Hall effect and the resistivity. Okay, people, because finally at the end of the day, electrons are only responsible for the observation of anomalous Hall effect as well as the resistivity. So how do we understand this? What is the scaling between these two fellows? So there is a theoretical open challenge, and also experimentally people have not done so far. For the first time we have done this, and then we try to show the relation between this. I'll not go into these details. These are very detailed mechanisms which involve anomalous Hall effect and all. So we try to understand what are all the responsible mechanisms for this kind of a thing. And then, as I told you, we actually did resistivity measurements, tried to understand using different theoretical models which are predicted, and then separate it out. And similarly, we did for magnetoresistance, anomalous Hall effect, we did these kind of measurements and then tried to separate it out and then got it. Tried to scale these relations. This is for some other time. I'll not have time to discuss this. But let me conclude. Actually, it has been a long day for you guys, almost 3 hours magnetism. But I hope that I could convey some enthusiasm to you, and I'll be happy to answer any questions. And I would like to, of course, acknowledge the people who have contributed for this work. This is my student who has carried out the second part of the work. In fact, okay, Binay Krishna Hajra. He is now working as a postdoctoral fellow at Max Planck Institute in microstructure physics, Germany. And Professor Kaul is my actually PhD thesis supervisor and also a colleague over the years after I joined here. And so I enjoy always discussing with him. And so I would like to acknowledge him for his inputs in this work. And also I have collaborations with Dr. Manuel Raja's group at DMRL, and team of scientists from IUC Indo, Rajiv Rawat, Archana, and Venkateshwar Reddy, Raghavendra Reddy, from UGC DAE CSR. And I thank you all for your patient listening, and happy to answer any questions that you may have. And yeah, thank you. I have to stop now sharing. Yeah, thank you. So I am done, and back to you, Vijay Kumar.
Participants are requested to raise their hands if at all they have any questions. Sir, Vijay Kumar sir, you're not audible, sir. Vijay Kumar sir. Sir, Vijay Kumar sir. Vijay Kumar sir. Yeah,
Maybe he'll reconnect again. I don't know.
Sir, I think it's again reconnecting, sir. Participants are requested to raise their hands.
Vijay?
Yes, sir.
Yeah, am I audible?
Yes, sir.
Yes,
Now
yes.
you are audible.
Yeah.
Now we can.
Two hands are raised. You please see.
Yes, sir. Dr. Sunil Dongre.
Yeah.
Good afternoon, sir.
Yeah, good afternoon. Who is this?
Sir, thank you very much. Very nice lecture delivered by you, sir. You very informative. I have no questions, sir.
No,
Thank
where
you,
are you from?
I'm from Maharashtra, Nagpur.
Maharashtra, Nagpur. See, normally in a class, what we say is when there are no questions, only under two circumstances. Either you have understood everything or you have not understood anything. So I hope that you have at least understood some things, right?
Yes, sir. Yes, sir.
Yeah, thank you. Thank you. Yeah, any other comments, questions?
Yeah, Dr. Jyoti Ranjan Sahu.
Yes, sir. Hello.
Yeah.
Sir, actually, I have a question that my first question is that while explaining the blocking temperature, you showed that the value of ZFC is negative. What does it interpret, sir?
Yeah. Okay. See, certain systems, what happens is the local anisotropy can make the magnetization point in a direction which is not along the applied direction. Okay, because you have cooled the system in the zero field. So the spins, because of the local anisotropy, they can choose to randomly orient in any direction. But when you apply a magnetic field, the magnetic field that we applied is very small, of the order of 100 Ørsted or so. That field may not be strong enough to point this magnetization along its direction. Only when you increase the temperature, then what happens is the spins will now start orienting along the magnetic field direction. So initially, but one has to be very careful. One has to do very careful measurements, because many times what happens is because of the residual field or remnant field also you will get. If the residual field is also stronger, and that is decided by your history of the system. If you are done too many high field magnetization measurements, and there may be a residual field which may be pointing in some other directions. Okay, so one has to be careful in interpreting this. But in our system, in our case, what has happened is because of the local anisotropy, that the magnetization initially was not along the field direction. Okay.
Instead of 100 Ørsted, if I take 1 Tesla, then
yeah, definitely it will switch. It will not even 1 Tesla. You just apply of the order of few kilo Ørsted, you immediately will see that the magnetization will be positive. Okay.
So my second question is, that regarding the magnetocaloric effect.
Yeah.
There you told us that because of the high value of magnetic field that is required, the magnetocaloric material are not practically useful. Rather, you opted for the superconducting material. You said for the superconductor material to prefer, because the high magnetic field is practically not possible to use. So, but in case of a superconductor which are actually perfect diamond, how can we have the transition? I mean, minus delta SM.
You're getting confused. Sorry. No, there is a confusion. I'll tell you. The active material is ferromagnetic material. What I want is to apply the magnetic field only. I am applying instead of electromagnetic.
Okay.
So don't get confused.
Sorry.
Then
I'm sorry. Okay.
Yeah, it's okay.
Sir.
It's okay.
Okay. So my another question is that so there are various factors associated with magnetocaloric effect, like minus delta SM, delta TAD, relative cooling power, refrigerant capacity, etc. You told. There, sir, how can you decide like which is a very good magnetocaloric material? Because some of the compounds like show minus delta SM so high, we are not showing delta TAD for that compound.
See, then, at the end of the day, what matters?
And relative cooling power also may be very high, may not be high also.
Yeah, good.
That is
very
another
good.
case.
Nice, good. I am happy that something we definitely conveyed. I am very happy for this question, because at the end of the day, I'm not sitting in a empty space. I am sure that you are listening very carefully. Very happy. See, your question is very good. Delta SM is like a qualifier, I would say. Okay, if we basically entropy change is basically tells me that the material is good to look at or not. Of course, one has to finally, to deliverability, you have to look at the delta T, how much it is transforming into delta T. Okay, for a single material, delta T is actually good. But if you want to really use for efficiency wise, cooling efficiency is not just decided by, like if I have a delta function which is a very large value delta T, but then the range over which this is operating temperature is so small, then I will have a practical limitation. Okay, when the temperature slightly goes up or down, then I have to bring back the system to that and then be able to do it. So in that sense, it will set up a practical limitation. So in the other hand, if I have a range over which I can operate, okay, then that is good for cooling efficiency. So for a given application, of course, one has to choose what is appropriate. Okay, if your aim is only to go to change in temperature, then probably delta T is alone is enough. But if you want to use it as a cooling machine or cooling load, then you need to have a cooling power. That is ultimately that is a deciding factor. Okay,
So,
and
but-
entropy
but-
change is only qualifier. You basically,
Okay, sir.
because the delta T measurement is very cumbersome, so people will routinely can screen materials. Okay, which one is good based on delta SM. Okay, that is why I try to give a flavor. I mean, introduce to everything. Right?
Again,
Yeah.
sir, my doubt comes now between relative cooling power and that refrigerant power, refrigerant capacity something.
Yeah.
So what is the basic difference between those two? Moreover, you have given the limits T1 and T2. How will you choose that T1 and T2?
No, it's a thumb rule. Again, I'll tell you. This is basically mostly is like full width at half maximum is what is used.
Yeah, that
Okay?
is for relative
So,
cooling power.
relative
But
cooling.
for refrigerant or capacity, delta SM dt with limits T1, T2, what does that indicate, sir?
Okay. See, okay, very good. That is basically when you are actually measuring delta M by delta T into delta Q, integral over, right?
Yeah, delta SM dt with
dt.
integration T1 to T2.
T2. So in what ranges? Because usually what I do measurement is how I do a measurement. I have to tell you, I do an isotherm called. That means I will fix the temperature constant and measure magnetization as a function of field. Okay. So I'll get one isotherm, like right, and then I go either depending on the protocol, either go to the higher temperature or low temperature and do the same measurement. So now, what is the cooling efficiency? Is the area enclosed between these two curves. So where is the limit I am talking about? So what I will do is I'll from this T1 to T2. Okay, so this is different from this is basically this becomes one data point for my delta SM versus temperature point. So I do this at a number of temperatures. Then I get basically a Gaussian or a Lorentzian. Then the efficiency is between that points. Okay, these two are two different. The first one is to measure delta SM at a given temperature. So at a given temperature, how do I measure? I have to compare with something else. So which temperature I'm comparing? So I will take one temperature prior to that or just after that, and then I will ensure, okay, midway these two temperatures is my delta SM so much. Then I go to the next temperature thing. I go on collecting these points. Okay, this is basically a cumbersome measurement. I have to do it, over a number of temperatures, get delta SM at each and every temperature, then plot delta SM versus temperature. Okay, then I know what is my operating temperature.
And sir, you told about thermal hysteresis. So while collecting or while measuring the isotherms, so either way you can go. I mean, from low temperature to high temperature.
That is, see, preferably speaking again. That's a very, very good question. See, if you are not working about thermal history, I mean materials which do not have any structural transition, then they do not have so much of thermal hysteresis. So I don't really care too much. Okay, but for magnetic history purposes, always it's a good idea to go from one reference to another one. Okay, either from lowest temperature to room temperature or vice the other way around. But if we are working on systems which have structural transition, then one has to be extra careful, okay? Because there is a thermal hysteresis associated with that. So the measurements have to be done with very, very low, I would say stabilized mode, in the sense you have to give enough time for the system to equilibrate, okay? So that whatever latent heat is there, that is, like dissipated or absorbed and all that, again get back to the same temperature, then do it. Okay, otherwise
So
you will get erroneous
you can
results.
start from low temperature and measure all the isotherms to room temperature, or vice versa, from up temperature to down.
But every time you need to ensure that you are actually in thermal equilibrium with the system. It cannot be done in like a sweep mode. I cannot do for I go on measuring it, because at that time your sample temperature is different and your system temperature is different and you get completely wrong.
Okay. So I have one more question from Hessler LS. Sir, sorry to kill your time, sir.
No, not killing. I'm actually enjoying. See, after 3 years, if people are responding, you feel very happy. I mean, as a teacher, you feel that you are done job. Okay, correctly. Good. Ask me.
Sir, generally when we synthesize the compounds, basically oxides, then in ordinary conditions, ambient conditions, we synthesize, and since it captures oxygen from the atmosphere, then later we annihilate in oxygen atmosphere, then our job is done. But in metal alloys formation, how do you decide? I mean, it will automatically capture oxygen.
Very good question. In fact, that is the most challenging or difficult job. Okay, because you need extremely high vacuum system to start with, because any trace of even ppm level of oxygen or something in the system, the chamber, will kill your system. You will not be able to get a metallic film. Metal means mostly it gets oxidized. You get, as I told you, I want to deposit a cobalt film and I get cobalt oxide, then it is an antiferromagnet, so I don't get anything. So, okay, that is the most challenging thing. Second thing is, to answer your question, when I'm changing the temperature, what I'm trying to see is I actually substrate is already loaded, everything is done, degassed and high vacuum is achieved. So here what I do is I keep the temperature of the substrate at certain temperature, high temperature, whatever I want to do it, instead of room temperature. Because room temperature, what happens is, for the people who have not knowledge, do not have knowledge, this the atoms will at high temperature will come and sort of bombard the substrate, and they get immediately they lose. It's like a quenching. So it gets randomly arranged. So you get an amorphous film. But on the other hand, if you keep the substrate at like 400 degrees centigrade or 500 degrees centigrade temperature, then what happens is you are not allowing this thermal energy or kinetic energy of the system to immediately come to rest. So you are actually allowing this flow to dissipate this energy in a controllable fashion, so that these atoms will have enough time to sort of relax and occupy their respective crystalline positions, so that you get better and better ordering. Okay, so that is what is the substrate temperature, but this is done in the chamber in vacuum, right?
Oh,
And then the second thing is, if you still are not very happy, you can keep this temperature for certain more time. Okay, and whatever you need to do, you have to finish it in the chamber only. You cannot take it out and then do it. Okay,
Okay.
that is first point.
Okay.
Second point is, before even if I take out the sample outside, I normally put an capping layer such as tantalum or something like that, so that I do not, once I take, because for all my measurements later, I have to take it out at room temperature. I break the vacuum, take the sample, and then go for magnetization, transport, or Kerr effect, FMR, whatever I want to measure. So when I am doing this, whole measurement will take probably 2 years time, right? Because once you make the sample, first you get the proper to grow the films itself, it will take 1 year or more, because you have to optimize so many parameters and then do it everything. This is like a PhD work. The student spent 5 years in doing this work. Okay, even though I present it in 1 hour, right? So the kind is it takes so much time, and once you do it, this film has to stay for such a longer time. Okay, even if you put in a desiccator and all, it will not sell. So you have to put the capping layer inside the chamber, make sure that there is oxidation is removed, is completely eliminated, then take out the sample, right? So then
Okay.
it is already 1 nanometer, 2 nanometer thick capping layer is there. This will not allow the film to further oxidize.
Okay.
Yeah.
Thank you a lot, sir. Thank you. Your patience and beautiful enlightenment.
Thank you very much, Srinath sir, for your
Yeah.
patience in answering all our participants. So always I prefer to listen your session among all the sessions in my course,
No, that's
whatever
fine.
the
Okay,
course is.
okay, fine.
But I am enjoying really. So you imparted the participants a lot from this 3 hours. Thank you for your kind support always. Thanks a lot. With this, I'm closing this morning session. And again, dear participant, please come back sharp by 2. Thank you, sir.
Okay, thank you. It was my pleasure. Thank you, Vijay. Thank you. All the best to the participants. Okay, thank you. Yeah, bye.
Thank you. Thank you.